People sometimes ask, what do you have to do to get a Nobel Prize? And my answer to that is wrong question. They said, why don't you fool around with these laser things, see if you can come up with something that's good for measurement. And the answer was laser cooling. If you shine light in such a way that it opposes the motion of the atom, then the atom will slow down.
At the time, what was your thought process? Were you like, this sounds mad, or I want to try and...
This looks like it's going to be a lot of fun. It's got to be good for something. Let's do it. And we made the best clocks in the world. We accidentally saw that the atoms were getting colder than what the theory said was possible. I mean, that's colder than anything had ever been made at the time.
How did you initially think of that?
The one was the best measurement of this one thing that had never been made. It's still the best measurement. Nobody has repeated it since. And that was 50 years ago.
Those things, they don't come around that often. It's amazing to be involved.
I started working on something that led to the redefinition of the kilogram. I'm very proud of that.
Because you read about that, in history books and stuff, but you're like, now I'm in that point in time that people are going to read about this.
And were it not for atomic clocks, we would never have had GPS. The lower you are in the gravitational field, the slower the clock runs. It's sometimes called the gravitational redshift. Today, the clocks can resolve that much difference in height due to Einstein's theory of general relativity. The size of the electron is 0. Yet, somehow or other, the thing is spinning. You can be in two places at the same time. You can be up and down at the same time. The atom is in a superposition of being everywhere, not just two places, but a gazillion different places. The thing that really freaked Einstein out is what we call entanglement. If you measure this one to be up, the other one's going to be down. How can it know to be down because it's so far away?
Yep.
Nothing can communicate between these two things. He said, no. This is just totally crazy. He didn't believe that God plays dice with the universe.
And so what did that reveal then in terms of...
Well, it revealed that finally you could put to rest that
Yeah.
Einstein just had it wrong.
It would be remiss of me to not go into quantum computing. They're scared that people are now gathering data from classical computers.
You've got a quantum processor that can decrypt it. People are now using quantum proof encryption methods that cannot be broken by quantum computers. And NIST has been a leader in that.
You've achieved a lot of great things, Nobel Prize and everything else. What keeps driving your curiosity beyond that?
Well, the advice I usually give is...
Welcome back. My guest today is Dr. Bill Phillips, a Nobel Prize winning physicist and one of the world's leading experts in laser cooling and atomic physics. Bill spent his career at the National Institute of Standards and Technology in the United States, where he and his team did something that textbooks said was impossible. They cooled atoms to temperatures colder than anything that had ever existed, hundreds of times below what the laws of physics said you could achieve. That work didn't just win him a Nobel Prize. It laid the foundation for more advanced atomic clocks, GPS as we know it, and the quantum computers that are being built right now. But here's the thing about Dr. Phillips. He never set out to change the world. He set out to satisfy his curiosity. And he'll tell you that's exactly the point. That the biggest breakthroughs in science never came from chasing outcomes. They came from people who were just genuinely obsessed with figuring things out. Whether you're a scientist, a student, an entrepreneur, or someone who just wonders why the world works the way it does, this conversation will remind you why staying curious is the most important thing you can do. If you're enjoying these conversations, a subscribe, like, comment, and share will genuinely help this channel grow. Thank you. And now, here is my conversation with Dr. Bill Phillips. Okay, yeah, like whatever the final year exams you have before you go to university. So physics was one of my subjects.
Yeah.
And I was highly enthusiastic about it.
Yeah.
But the problem was I was not great at math. And a lot of people think that it just goes hand in hand. If you're good at physics, you have to be good at maths. And I really did struggle with maths. I did pass, which is the kind of lower level. Everyone else in my class was doing honors maths, which is the kind of higher level. So I did struggle in that aspect. But I think what kept me going was, and this is something you touch on a lot, is if you maintain that curiosity, and if you kind of maintain that wonderment, that childish wonderment, and if your teacher is someone who kind of can keep you engaged in unconventional ways, which is something I heard you speak about as well. It's not just the kind of run-of-the-mill teaching. If they find interesting ways to keep you engaged, and that's what my teacher did.
Yeah.
And that's a shout out to Mr. Tim Fennell. Thank you, Tim. And since then, you know, I did struggle a lot with concepts, but it wasn't for lack of enthusiasm. It was kind of maybe the maths or something else. But I guess kind of from your background in terms of like your curiosity, and as a kid growing up, you were probably a lot into experimenting with things, tinkering with things.
Exactly. And I've always felt I've always thought of myself as being an experimentalist. And as I learned more physics and learned more about what was involved, I decided I would never have the mathematical sophistication to be a theoretical physicist. And it solidified my understanding that I really should do experimental physics.
Okay. So you knew early on that you had maybe... You knew what you were good at and what you could maybe thrive at. So you said, I'll put that aside and I'll work towards this aspect of physics.
Yeah, in fact, I would say that I was unusual in the sense that in the U.S., perhaps differently from a lot of situations in Britain or in Western Europe, many people go to university imagining that they're going to do a particular thing, say major in physics or major in math. And very rarely do they actually do that. Do they finish their 4 years of undergraduate studies with a degree in the thing they thought that they wanted to do when they got there? I did. I went thinking I wanted to do physics, and I stayed with it the whole time. None of the people who graduated with me with degrees in physics started in physics.
Okay, gotcha. Okay, so you always knew from a young age that...
Yeah, I did, which I think is unusual, at least in the States.
Yeah, sure. And I read a quote somewhere, I'm maybe paraphrasing a bit, but it was kind of a nice little lighthearted comment that you made about the different disciplines of science.
Yes.
Which was chemistry is icky?
No, chemistry is stinky.
Stinky.
And biology is icky. Now, it's sort of a joke to sort of explain why physics, because I was interested in everything scientific as a child. In fact, I think all children are naturally interested in everything. I think that one of the deficits of our typical education system is that we tend to squeeze that curiosity out of people.
Yeah.
And I've often said that the people who have resisted that are the ones who become scientists.
Yeah, exactly. Yeah, because you're saying that they squeeze the conventional institutes.
Yeah.
For somehow they squeeze that out of people.
So it seems. That is, when I, and I love to do this, when I go and talk to a kindergarten class, they are just so enthusiastic about everything that I have to tell them. Whereas if you go to a class of high school seniors, a lot of them are going to sleep through the...
Sure. Yeah. And it's kind of pulling along that thread of childish wonderment, because you're revealing things, fascinating things in nature, in physics, that people, in a kind of a very visual way, you might be doing an experiment, you might maybe like a liquid nitrogen experiment or something like that, and when they see, it's the whole theatrics of it. I think physics is very theatrical. And that's...
Well, at least the way some of us do it. So, for example, take liquid nitrogen. I use it all the time when I give talks. In recent years, I've had to develop very careful protocols to make sure that everybody's safe when I do this. But liquid nitrogen fascinates young children. And if I didn't do something to prevent it, every kid in a kindergarten class would be on their hands and knees on the floor looking at the liquid nitrogen that's skittering across. Whereas if you do this to a room full of adults, they'll recoil in horror at the idea of the liquid nitrogen because it's something different. But that's, of course, what attracts the children, is the fact that it's something different.
Yeah, and it's I guess because they haven't, and it's a kind of a nice experiment in sort of human nature. You know, adults, they've been through things and they've seen that certain things are dangerous. You don't do this, but kids, they don't have that yet. They still have that wonderment. So it's like, can I put my hand in this? Can I touch this? Can I? And it's great. Obviously, you said you have to have guardrails.
Sure, we don't let the kids do that.
Yeah. No, that's great. And I think that's what kind of pulled me through it, even though I sort of, the odds were a little bit against me conventionally with not being great at maths.
Yeah.
But there's a lot of, like Sir Roger Penrose, he famously says that he was not great at maths. There's plenty of other,
which is interesting for a theoretical physicist.
Yeah, and he admits that, and I think was it Richard Feynman? I don't know, was he famous for being very good at mathematics? I could be wrong, but I'm pretty sure I read somewhere again that a lot of these guys, they admit that they're not, that they weren't brilliant at maths, but they had that curiosity to kind of get over that. And was that something that carried you through with when you struggled with, like, say, mathematics or anything?
I wouldn't say so much that I struggled with mathematics.
Okay.
I was good enough at it that I could get through all the courses, but I could also see that the more sophisticated versions, the kind of thing that I would be reading about in textbooks or in research papers, would involve a level of mathematics that was beyond what I was comfortable with.
Okay. Gotcha.
And so I've been very happy to have as collaborators people who are really good at that sort of thing. And in particular here at NIST, it's really been wonderful to have on-site theorists who are interested in understanding the kinds of things I'm doing in the laboratory.
Right.
And from their point of view, they're very happy to have experimentalists who are interested in trying out in the lab things that they've figured out on mathematically.
Okay. Yeah. So you complement each other very well.
Exactly. That's been one of the great joys of doing physics here.
Sure.
Is that connection between experiment and theory.
Okay. Interesting. And you you didn't initially start the conventional route. You went to Juniata College?
Yeah, so Juniata College is a small liberal arts school, which is to say that the nature of the education is quite broad.
Okay.
This isn't to say that they are ignoring the sciences. In fact, they were very well known for having a very strong chemistry program, for example. But at the same time, they thought it was essential as part of your education that you understand things in the humanities, that you learn how to write well.
Right.
In fact, one of the things that was different about Juniata compared to most colleges, most colleges, all freshmen were required to take, at least at that time, a course in writing to basically learn how to write.
Right.
Whereas what Juniata did was every freshman was required to meet with a faculty advisor who would advise them about the writing that they had done in other classes.
Okay.
So that you were learning to write as you did your writing for other things. It created a kind of a unity between the different classes that you were taking that was intersecting in good writing.
Okay.
And that background that I've had has, I think, served me very well as a physicist, because writing scientific papers is one of the key things that you do as a scientist. It's one of the most important ways in which you communicate your scientific results to the general scientific community.
Sure.
And so doing that well is really important. Well, I was taught to write well, to be very careful. That education continued in graduate school because I was fortunate enough to have a thesis advisor who also valued writing very highly.
Sure.
And so when I came here, I continued that, and when writing papers, and I was almost always writing papers with other people, we would sit down and go over the paper, and we still do this very carefully, sentence by sentence, to make sure that every sentence was saying what we wanted it to say, and that it said it in a way that was clear.
Okay.
This procedure became affectionately known as paper torture.
Okay.
Because
Yeah.
it was
It's like
long and drawn out and
pulling teeth.
sometimes painful.
Yeah. Okay. So it was just very stringent. And I guess that's a skill in itself, seeing how you put yourself in the eyes of the people who are going to be reading it. So
Yeah.
you kind of need to have that sort of empathy to say, okay, if I'm in this person's shoes, am I going to be able to understand this?
Exactly. And so we ask ourselves, well, will someone who isn't familiar with the jargon that we use in the laboratory every day, will they understand what this means? And if not, then we'll write it in a way that is
Sure.
self-explanatory. We often will ask ourselves, will someone who is not a native speaker of English understand what this sentence says?
Okay. So you have to think of a lot of different sort of facets of communication. And do you think going to Juniata kind of really helped you bridge that gap in terms of?
Yeah. I'm very happy that I did that, that I went to a place like Juniata and got that kind of a broad education, and then went to MIT for graduate work. MIT is sort of famously focused on scientific and technical things. I'm glad that I was not an undergraduate at MIT, but very glad that I was a graduate student there.
Okay. And do you think going to Juniata first, do you think that helped you to maintain that kind of curiosity? Instead of, we say like institutions can sometimes squeeze that out, but do you think that helped you to really, did it give you the space to experiment, to kind of play and to?
Yes, it did. But I think that the curiosity that I had was already fairly well baked into me by the time I went to Juniata, because as a boy growing up, I was constantly experimenting and following my curiosity in ways that I think set the tone for my professional life. When I think back to the kinds of things that I did as a boy, it's amazing that I didn't hurt myself much more severely.
Thank God.
But, well, for example, one of the things, my father helped me build a sort of a workbench. And because I was going to be doing experiments with flames and with chemistry, cooking things, and with physics, heating things up and seeing what happens. We lined the surface with asbestos.
Oh wow!
This is before people knew how dangerous that was, and somehow or other, I've survived.
You might have built up an immunity.
In spite of that, but well, I doubt that. I don't. But and I had a chemistry set of the sort that you could buy. You could buy a chemistry set, and it came with all of these chemicals that you then would have instructions about how to use them to see certain kinds of chemical reactions. I'm pretty sure you can't buy anything like that today that has all of these dangerous chemicals as part of the stock of the thing that you would buy. And in a certain sense, I think that's too bad, because it limits the kinds of things that young people can do.
The level of experimentation that you can do.
Yeah.
And at that time, kind of, if you can go back into your head at that time, were you experimenting just kind of for the love of seeing where this will go in terms of the unknown, or were you trying to kind of get to a result?
More to just have fun.
Yeah.
The way I developed as a boy was that I thought this was one of the great ways of having fun. Now, it's not like it was the only way that I had fun. Like all the other kids my age, I would, we'd get together with a team of people and play ball. I would spend hours just walking through the woods and picking huckleberries and eating them, and just observing the kinds of things that you see in the woods.
Sure.
And one of the things I think about often is that the kinds of things my parents would let me do, and that all parents of that era let their kids do, would today be considered child neglect.
Yeah.
That they said, well, make sure you're home in time for dinner. And I was.
And you don't see them for 8 to 10 hours.
Yeah. And I didn't have a cell phone.
Yeah. You just use the weather and you use the daylight to Yeah, and I think these days, yeah, you're saying people might call Child Protective Services if they see a kid walking down the street on their own, but that was kind of a different
But I'd
time.
been taught,
Yeah.
I'd gone on walks through these same woods
Mm-hmm.
with my parents. So it wasn't that I didn't know the woods and I
Yeah.
didn't know what kinds of things you encounter
Mm-hmm.
when you walk through the woods.
Sure. Yeah. Yeah. No, that's fair. And what age around did you kind of get into the experimental aspect, the science aspect of play?
I would say by the time I was 5 or 6 years old.
Wow.
So one of the things that I remember very clearly is that when I was on the order of 5 or 6, I got a microscope as a gift. And I can remember collecting all kinds of stuff from around the house.
Okay.
You know, dust and insect parts and stuff, and looking at them in the microscope just to see, what did this stuff look like under a microscope. And I can remember before I had a commercial chemistry set, just making little bottles full of household fluids, milk and orange juice, and seeing what would happen when you mix these things together.
Sure.
So that was from a very early age.
Okay. Okay.
And then as I got older, my parents would always be very supportive and encouraging of my exploration, and they would get me more sophisticated things, better microscopes.
Nice. Okay.
Full-blown chemistry sets,
Yep.
physics sets, things that would allow you to make pumps and
Wow. Okay. That's great, because it's if you have parents that encourage that really, because you could maybe have the opposite sometimes, where it's a bit discouraged in terms of maybe safety, or they just But it's good that you have parents that really encourage that.
I mean, again, one of the things that, thinking back, obviously wasn't very safe, but one of my friends had learned how to make what's called a carbon arc. Now, I don't know if you know what this is, but it used to be one of the ways in which people would make an extremely bright light source. It would be used in things like projecting movies, for example. Well, the way in which I implemented a carbon arc is that I got 2 little sticks of carbon, which I got by opening batteries, So you take most of the batteries aren't made that way, but this was a particular design of battery that was the most common thing back in those days. And it had a center rod that was carbon. And so you get one of those, you get 2 of those, and find a way of holding them in a way that insulates them from electricity, and then hook up each of those to a source of electrical power, which in this case was plugging it into the wall. Okay. But in order to limit the current, you had to send it through a resistor. Right. So that it would limit how much current could be drawn, because if you just hooked it up to the wall and touched the electrodes together, it would short the thing out, and that would, blow the fuse for the circuit. Yeah. So instead, we would, and the way we made the resistor was we had a big jar of salt water. Now, salt water will conduct electricity, but not particularly well. And then we put pieces of metal in there, we would call electrodes, and that would, so then you take these 2 pieces of carbon that are hooked up to these wires that are ultimately connected to the wall. And, we were very careful to make sure everything was insulated, but it wouldn't have met NIST standards of safety. No. But, I was 10 years old or something when I was doing this. Okay. So, and what we do is touch the things together and then pull them apart. And even though they're not touching anymore, an electrical current would flow between them by ionizing the air, creating what we call a plasma, an ionized gas. And that light was extremely bright. So this is why, these kind of devices had been used for such a long time as a really bright light source. And then you'd pull it apart, and the spark or the plasma between them would get bigger, more light, pull it further apart, and then it couldn't sustain it anymore, and it would stop. So then put a little bit more salt in the water so to conduct more electricity. Now you can pull it apart even further, get it bigger. So at some point, it did blow all the circuits in the house, but somehow my parents forgave me.
Well, that's the whole That's the whole joy of the experimentation. You push the boundaries.
Yeah.
You're like, how much can I get away with this? How far can I go? And that's I guess the whole core concept of.
Well, exactly. I don't know of any experimenter who wouldn't, if they've got an instrument in a lab where you can turn up the knob,
Yep.
would not turn up the knob all the way to see what happens.
Yeah. It's kind of like don't press the big red button, or it's human nature, and it's that curiosity that you're like, how far can we go with this?
Yeah. And in my field, we have learned really important things by going to the extremes.
Yeah.
In our case, the extreme was the coldest stuff you could get.
Yeah.
And for other people, it's been the highest intensity laser you could get. In other experiments, the hottest thing you could get. In fact, at one time at NIST, my laboratory was at one end of a rather long hall where we were making the coldest stuff in the universe. And at the other end of the hall was another group of people whom I knew very well who were making the hottest stuff in the universe. That was pretty cool.
Yeah. Wow. So it's just the two extremes.
Yeah. And we were both using spectroscopy, that is looking at the light that comes out of this system as the way of learning what was going on, which is kind of interesting that what was essentially the same technique could allow you to learn about both the coldest stuff and the hottest stuff.
The hottest stuff. And it's, I guess, directly proportional to the temperature is directly proportional to the frequency.
Well, the temperature of a of any substance is basically a measure of the kinetic energy of the stuff that makes it up.
Okay.
So if we're talking about a gas, then temperature is a measure of the kinetic energy of the atoms and molecules that are moving around in the gas. And the kinetic energy is 1/2 mv squared, where m is the mass of the atom and v is its velocity. And temperature is just a different constant applied to 1/2 mv squared. In fact, one of the wonderful beauties of recent times is that we have reformed the metric system, the system of units that we all use to measure things and express our measurements.
Sure.
We've now defined temperature, so it's explicitly related to the thermal motion of the things that make it up.
Okay, so it's
it would change the definition of what a Kelvin means, the unit of temperature, in 2019. And in fact, the thing that I'm wearing on my lapel is a color wheel that shows the 7 base units of the International System of Units, which is the official name of the metric system.
Okay.
The Système International, which is why it says
which is
SI.
is the French?
Yeah, because it was started, French is the diplomatic language of the 19th century, and it all started.
Wow. So pre-2019, how was...
Exactly. So pre-2019, the Kelvin was defined to be 1/273.16 of the triple point of water.
Okay.
So the triple point of water is a certain temperature, and the amount by which it is above absolute zero is defined to be 273.16 degrees, or it was up until the 20th of May, 2019. Now, the 20th of May is a very special day because it's World Metrology Day.
Okay.
And why is it World Metrology Day? Because in 1875, the countries of the world, or at least 17 of the countries of the world, got together and signed a treaty, which is known as the Convention de Mètre, the Treaty of the Meter, in which they agreed to adopt the metric system and to establish an International Bureau of Weights and Measures, what we call the BIPM, the Bureau International des Poids et Mesures, and to support that to maintain the standards of the metric system. And it's still in business, and we still support it. And we just celebrated World Metrology Day about a week ago, and I get to talk here at NIST about the reforms that happened just in 2019.
Okay. Wow.
And that was one of the reforms, was that instead of the Kelvin being defined as being 1/273.16 of the triple point of water, we now define the Kelvin by defining Boltzmann's constant. Okay. Now, what is Boltzmann's constant? If I take the temperature of something
Yep.
is measured in kelvins
Mm-hmm.
and multiplied by Boltzmann's constant,
Okay.
then I get the energy that that thing has in its individual atoms and molecules, how much kinetic energy they have. Well, I mean, there's a factor of 1/2 or 3/2 depending upon whether you're in one dimension or in three dimensions. But basically, Boltzmann constant is the thing that converts energy as measured in kelvins to energy measured in joules, which is the usual way of measuring energy.
Okay.
So we've now defined temperature as that thing that converts you between joules and Kelvin. So it's much more fundamental.
Okay.
It says if you know what's going on at the microscopic level, then you know what the temperature is. You don't have to think about all this stuff
Variables.
about the triple point of water, and you can. Now it turns out that we measure things the same way we used to because we haven't quite gotten good enough to measure directly the kinetic energy, but we're working on it.
Okay.
And I don't think it'll be that long before that becomes the primary way in which we measure temperature.
Right. Okay. So you're saying currently it's slightly an indirect way of measuring, but you're
Just a little bit.
Okay.
Yeah.
It's kind of deducing from certain variables.
Yeah. See, the way it's done now is using something called an ideal gas thermometer.
Okay.
And the idea is that, as you probably learned in your first physics course, that there is a thing called the ideal gas law that says the pressure times the volume is equal to the number of moles of something times the molar gas constant times the temperature. PV equals nRT.
Okay.
Okay. Well, that universal gas constant is just the Boltzmann constant times Avogadro's number, which you may remember is the number of things, the number of, say, atoms that are in 1 mole. And we define that to be the number of things the number of carbon atoms that are in 12 grams of carbon-12. That's the way we define what a mole is. A mole of anything. It's something that has that number of things in it. So if it's oxygen molecules, then it's that number of oxygen molecules is a mole of oxygen.
Right. Mole of oxygen.
Yeah.
Okay.
But now that used to be the definition of a mole. That a mole is the amount of substance that has the number of things, whatever you're talking about, oxygen, nitrogen, carbon, gold, whatever, it's the number of it's the amount of substance that has the number of things, elementary things, that's equal to the number of carbon-12 atoms in 12 grams of carbon-12. That's what it used to be.
Okay.
But now it's just a number.
Right.
We've defined what a mole is by defining what is still called Avogadro's number.
Okay.
That number, the number of things that's in a mole, has been called Avogadro's number for decades or centuries.
Okay.
And now we've just defined what Avogadro's number is.
Okay.
Instead of making it a measurable quantity.
Right.
And all this happened along with 2 other really important measures, the kilogram and the ampere, have both been redefined
Okay.
as of the 20th of May, 2019. And in fact, when I first came to NIST, I started working on something that led to the redefinition of the kilogram. I'm very proud of that.
Wow. You should be. Yeah. Fair play. Wow. Yeah, because those things, they don't come around that often. So it's good. It's amazing to be involved.
Yeah, that's right. When I give talks about this, I say this is the most revolutionary change in the metric system since the French Revolution, which brought us the metric system in the first place.
Okay.
Because it was the French revolutionaries who decided we needed a new set of measurements because we have all these crazy measurements and we need to unify this and make it something that is available to everybody, sort of in the spirit of égalité, liberté, fraternité. They wanted to have something that was available to everyone. That was the philosophy behind that.
Yeah.
And they invented the metric system.
Right.
And this, what we had in 2019, I claim is the biggest, the most revolutionary change since the French Revolution.
Wow. Wow. That's amazing to be kind of part of that.
Yeah, exactly. To be part of that here at NIST.
Yeah. Because you read about that, in history books and stuff, but you're like, now I'm in that point in time that people are going to read about this.
Yeah.
So it's...
Yeah. Now, I mean, that's what NIST does. I don't know if you know that much about NIST, but we are the what's called the National Metrology Institute
Yep.
for the United States. We're the ones who are responsible for guaranteeing that when somebody says this thing is, a centimeter across, that there's a way of guaranteeing that it really is.
Okay.
And we're the ones who have the responsibility of being able to guarantee that. In the UK, it's the National Physical Laboratory in Teddington.
Right.
And every big industrialized country has a National Metrology Institute, and smaller countries then have agreements with other metrology institutes so that they can also guarantee. So without that, international trade wouldn't really be possible in today's modern society.
Yeah, because people couldn't convert from the base units, and there would be just a kind of a breakdown in communication.
Well, you wouldn't be able to guarantee
Yeah.
that when you sold something to somebody and said, my screws have, are M6s, then who's
definition
guaranteeing that those
Yeah.
threads are as far apart as they're supposed to, and that the body diameter of that screw is what it's supposed to be?
Yeah, because it's like that. It's my definition might be different to this guy's definition,
and that's the way it was before the Convention du Mètre. That you would go to different places, and there would be cemented into the wall of the city hall a foot or a fathom or a yard. And that would be the length for that city. Now, that's a disaster if you're trying to do trade.
Yeah, because it's all based on the human body. You're using the human body.
Well, that was where a lot of things started. It wasn't all, but yes, obviously a foot was based on a foot. But at some times, the foot was the length of the king's foot.
Yep.
But at some times, the foot was 1/20th of the length that 20 men lined up would put their feet together, and then you would measure that and take 1/20th of that to be a foot. Now, that had the great advantage of averaging over, which is one of the things we do routinely scientifically, is to take average to smooth out variations. But of course, it still is going to vary depending on who you happen to get together to do that. So, NIST was formed basically to get rid of that kind of stuff. We'd already gotten rid of it. We had a Bureau of Weights and Measures before we had NIST, but NIST was, it became clear that in the modern era, NIST was formed, 125 years ago. So just about at the turn of the century. And manufacturing was getting so good that you'd better do it right. You'd better be able to measure things to a millionth of a meter, or things weren't going to fit together. So you had to have a really serious operation, and that's what the National Bureau of Standards, which is what we were called at the beginning.
Okay, wow,
was
National Bureau of Standards, and now NIST, National Institute of Standards and Technology.
Yeah. I think 4 standards in technology.
4 standards in technology.
Or is it of? I can't remember. Of, okay.
And just to kind of go back a little bit, so after Juniata, what type of experimentation did you get into initially into Juniata? Was it?
Yeah, well, one of the things was my freshman physics course, we had a lab. So for 3 hours every week, we went into the lab and did experiments on a wide range of things. Now, these perhaps weren't all that different from the sort of things I had done as experiments in high school, but more sophisticated, using more math, using better instruments.
Sure.
And I just loved it.
Yeah.
I just thought it was fantastic.
Yeah.
To see the kinds of things that we were learning about in class play out in the laboratory. Well, so my first year, I guess it was really my first semester there. I was just loving what I was doing, and I guess the teacher, who was a fantastic teacher, Ray Frogner.
Okay.
He just really fed the curiosity of the people who were. He would invite us to come back in the evening. Now, we were all living on campus in dormitories, and
Sure.
my dormitory was probably 100 meters from the science building. And he would invite us to come back in the evenings and show us movies of Richard Feynman
Wow.
talking about fundamental ideas about physics. And he would pop popcorn, and we would eat popcorn and watch Feynman talk about the character of physical law. Those were, I think, 16 millimeter films. Probably this was a couple of years after Feynman first gave the lectures. Those lectures are still really good.
Yeah.
If you watch them on YouTube, they still have that wonderful excitement that Feynman was able to bring to.
Yeah.
Well, anyway, so that was the kind of thing that he would do.
Sure.
Is to sort of feed our thirst for understanding physics better. Well, he must have talked to his colleague, who was at that time, I mean, there's only a couple of professors, and this other guy, Wilfred Norris, came to me and said, I think you'd enjoy doing this course that's called Junior Laboratory in Physics. So, because, I'm a freshman, and so I'm, first year student, and this is the chief professor in the physics department. Of course, I said, sure. Now, I thought that Junior Laboratory in Physics meant that it was, sort of a beginning thing. What I didn't realize was Junior Laboratory in Physics is what third year physics students took.
Oh, wow.
And I'm a first year physics student. Okay.
Yeah.
And there was nobody else doing it. It was just me and the professor.
Wow.
And and basically it was a series of classic experiments. So I was going to measure the Boltzmann constant, for example, in one of the experiments. I was, and there would be some apparatus, and he would explain to me how this worked, and I would go at it.
Wow.
And sometimes I would work for a couple of days and get hung up, and I'd go to him for some advice, and he'd explain to me what to do. And so I was learning how to use all of these pieces of laboratory equipment sort of in real time on my own. And it's one of the best ways to learn things.
Yeah.
So that was really cool. And then after I finished that, he said, well, would you like to participate in some of the research that I'm doing? And I started working on an apparatus that did what's called electron spin resonance. So any number of substances have atoms that have what we call an unpaired electron spin.
Sure.
So an isolated electron spins, which is kind of crazy in itself.
Yeah.
Because the size of an electron, as far as we know, and we have very good evidence for this, that the size of the electron is 0. That's the diameter of an electron.
Wow.
Yet, somehow or other, the thing is spinning in the sense that it has angular momentum, something that we're familiar with from macroscopic objects. You spin something, and sort of the amount of motion, the sort of rotational equivalent to momentum, which is mass times velocity. Here, and for something rotating, it's mass times velocity times the radius at which that mass is rotating. That's angular momentum. Well, these electrons that have no radius at which anything is, they have angular momentum, and you can see it, you can measure it. But because it's charged, it also means it generates a magnetic field. If I have a loop of wire, it creates a magnetic field. Well, a spinning charge creates a magnetic field, even though it's 0.
Radius,
So, but anyway, so if you put that spinning electron into a magnetic field, then it has a different energy depending upon whether the spin is pointing along the magnetic field or against it.
Okay.
Just like if you were to take a compass and put it in the Earth's magnetic field, it'll point in one direction. And it would take a certain amount of energy to have it point in the opposite direction. Well, the difference between those two energy states for an electron is something you can measure.
Right.
And measuring it is, the process of measuring it is called electron spin resonance, because what you do is you shine in a frequency of, say, radio waves or microwaves or light, depending upon what the energy difference is, which will depend upon the magnetic field or maybe other things. the structure of the atoms, and you shine that in. And when it's just at the right frequency, that is, you take the frequency of the microwaves, multiply it by a thing called Planck's constant.
Yep.
Another thing that we redefined in 2019.
Yep.
You multiply the frequency times Planck's constant, and that's the energy.
Okay.
So you tune the frequency until the frequency matches the frequency that will make you go from one energy state to the other.
Okay.
And that's called resonance.
Right.
And anytime you match frequencies, it's called resonance. And here, because you're doing it with an electron, and the spin of the electron, it's called electron spin resonance.
Right.
So I started working on electron spin resonance.
Okay.
Learned how to make and measure microwaves, learned how to put together waveguides that would transmit microwaves from one place to another. And then I got an opportunity to go to Argonne National Labs, which is outside of Chicago, and work with two guys who were doing electron spin resonance. Because, I knew a little bit about that, and it sort of made sense to work with these two guys. So I took one semester of my senior year in college and spent it at Argonne National Labs, working with two guys who did research all the time. That was their full-time job, doing research every day, all day. And I mean, this is what I do now. And this gave me an opportunity to see what it was like. And I thought, yeah, that's for me.
So they were doing the theory, and it gave you an opportunity.
Well, no, they were doing the experiments.
Okay, sorry, they were doing the experiments.
Just like I'd been doing back at Juniata, but more sophisticated.
Okay.
They were cooling things down to liquid nitrogen temperature so the spectra would look better. That is, when we would scan the frequency of the microwaves, we would make different spins that are in different places, in solids, would flip, and we'd see the results of that, and that's called a spectrum.
Okay.
When the thing was cold, the spectrum was so much cleaner and so much more simple because it wasn't affected by all the thermal motion of the spins, and so I learned how to use liquid nitrogen for the first time.
Wow. And
And one of the things that sticks in my mind so firmly, this one guy who was my main mentor said, now we're going to be using liquid nitrogen to cool these things down. So it's really important that you understand the value, the price of these cryogenic liquids.
Okay.
So he said, what do you think a liter of liquid nitrogen costs? Excuse me. And I said, well, this stuff is so incredibly cold. This must be like a few dollars a liter. And he said 3 cents, and he poured some of it out of the ground.
Wow.
And then he said, what do you think a liter of liquid hydrogen costs? Well, I knew that liquid hydrogen was way colder than liquid nitrogen. I said, well, that must be a couple of dollars a liter. And he says, 16 cents. Well, he didn't have any liquid hydrogen, but And then he said, so what do you think liquid helium costs? And I said, well, liquid helium, I knew it was even colder than liquid hydrogen. And I said, well, that must cost a couple of dollars a liter. And he says, yes, that's right.
Okay.
That's what liquid helium costs. So it really, it's one of those things that stuck with me. They had at Argonne National Labs to operate their bubble chamber. So a bubble chamber is a device that allows you to see the tracks left behind when elementary particles like protons or pions or whatever go through it. It'll leave behind a trail of bubbles, and that's why it's called a bubble chamber.
Okay.
And the thing you would often use in a bubble chamber would be liquid hydrogen or sometimes liquid deuterium, depending upon what you were looking at. Well, there were 3 huge tanks of cryogenic liquids outside where they had the bubble chambers. Now we've got over here, you could look and see a similar thing. So it's like 2 stories tall and,
Wow.
Maybe half the diameter of the length of this table.
Yep.
And we it's full of liquid nitrogen. Well, they had one of those, and it was written on it, liquid nitrogen. So it's got, a huge amount, I don't know what, maybe 1 million liters of liquid hydrogen.
Yeah.
And next to it was one that said liquid hydrogen. And next to that was one that said liquid deuterium. I thought, liquid deuterium? I mean, the deuterium is present in nature at the rate of 1 deuterium for several thousand hydrogens.
Oh, wow.
So it's pretty rare stuff.
Yeah.
And they had this immense tank. I was really impressed.
And how do they harness that, or how do they extract that?
Well, they just have a pipe on it.
Yeah. Okay.
Put it into a dewar.
Wow.
I mean, there's a transfer process where everything is very well insulated.
Okay. Gotcha. Wow. And so this place that you were doing the experiments, was that before, so that was in between Juniata and MIT?
Well, I went back to Juniata for one more semester after I finished that. But I think that was really important for me.
Okay.
Because it meant a couple of things. One was that I had people who were people who regularly published scientific papers writing me letters of recommendation.
Wow.
To a place like MIT
Okay.
that never heard of Juniata College.
Right.
Okay. So in fact, here's an interesting story, which I often tell, especially when I'm at Juniata.
Sure.
We would have people come from outside college to give talks, just like every university does. They have a regular colloquium. We didn't maybe have a regular one, but so a guy came and he was talking about astrophysics. He had gone to Princeton and he was now some other place. And as often happens, today we do exactly the same thing. He, after giving his talk, he sat down with the students just to talk to them about their futures, about careers in physics and about going to graduate school. And since he'd gone to Princeton, I said, well, I'd read, this is before you could just go on the web. There was no web. But there were books that were published by the National Academy of Science rating different graduate programs in physics.
Okay.
And at that time, Princeton was rated as having the highest rated program.
Wow.
So I said, I'd read this, that Princeton had the highest rated program. So I said, well, that's where I'd like to go. And he said, a student from Juniata College can't get into Princeton. I said, oh. Well, I applied to Princeton.
Yeah.
I applied to MIT, to Caltech, to Stanford, Berkeley, I think. And I got into all of them.
Wow.
Why? Probably because of my experience at Argonne National Labs.
Okay.
But the story that I tell when I go to Juniata is, so I went to visit Princeton to see what it was like. And I decided it wasn't what I wanted at all.
Okay.
Went to MIT and immediately clicked. This is where I should be.
Right.
I could just tell this was the kind of place.
Okay.
Especially not just MIT, but I was invited by a professor, Dan Kleppner, just passed away about a year ago. One of the great figures in atomic physics, a person who really defined what a whole era of atomic physics was about.
Yeah.
And he wrote to me, a letter, mailed with a stamp, because that was the only way you could do it, and said, I saw from your application information that you did some work in electron spin resonance. We're doing stuff sort of like that. Maybe you'd like to come and join our group. So I went and visited with his group, talked to some of the graduate students, and immediately understood this is where I needed to be.
Wow.
And that's where I was for the next 8 years.
Wow.
And it changed everything for me. I mean, it really set me on the path that I followed. It was the thing. So here's another funny story. When I went there, I started working on this problem, this project for electron spin resonance. We were doing things at a much higher level than what I was doing as an undergraduate. We were making really, really precise measurements. So one of the things that I did, which turned out to be a really important measurement, was to measure the ratio of the magnetic moment of protons in water to the magnetic moment of electrons in free space. And how did we do that? Well, there was hydrogen, and the electron in hydrogen is so close to being in free space that you could calculate the difference.
Okay.
And water, I just used water and measured it. It turned out that that was a really important number for experiments that were being done here at the National Bureau of Standards.
Okay.
They were measuring a thing called the gyromagnetic ratio of the proton. And it's almost like measuring the magnetic moment of the proton, except what it is measuring what frequency you have for the two different states of the proton, which is just like an electron. It's spinning, except it does have a size. And because it's made up of 3 quarks.
Sure.
Whereas an electron, as far as we know, isn't made up of anything. It's just an electron.
Yeah.
Okay. So proton has a spin. It's got a magnetic moment. And what I measured was the ratio of that magnetic moment to the electron. What they were measuring here was what's the frequency if we put it in a certain magnetic field, where we measure the magnetic field by making a coil of wire, and we know where all the wires are, and we know how much current we put in it.
Okay.
That's a really hard thing to do, because measuring where the wires are is really, really hard. But they did that. They were doing that better than anybody had ever done before. Okay? And why were they doing it? Because with a few other constants, you could combine them and find out what a really important fundamental constant of nature is, called the fine structure constant. Now, what is the fine structure constant? Well, I could tell you what it is in terms of other constants. It's E squared, where E is the charge of the electron, divided by 4 pi epsilon naught, where that's something that tells you about how strong electromagnetic forces are, or electric forces, and divided by the speed of light and Planck's constant. And why this? Because all those things together form a constant that is dimensionless. And that's really cool, that you've got something that basically is telling you in a dimensionless way how strong electromagnetic forces are.
Okay.
And the value of that thing is 1 over 137. 137 is sort of a magical number among physicists.
Right.
Because of this thing. It's almost exactly 1 over 137. Not perfectly, but when people first measured it, they thought, wow, maybe it's exactly 1 over 137, and had all sorts of reasons why, but it's not. But just by chance happens to be 1 over 137. So every physicist recognizes 137 as being a kind of wonderful number.
Magic number.
Well, anyway, why did we need to know that? Because you can calculate what the magnetic moment of the electron is if you know what the fine structure constant is.
Right.
And you can also measure it. Now, it is the most accurately measured thing of anything we ever measure. So why why? Because measuring it and then comparing it to the calculation tells you whether you understand the most basic things about physics.
Okay.
So one of the most basic theories of physics is quantum mechanics married with electromagnetism. We call that quantum electrodynamics.
Okay.
And we think that we understand it exquisitely well. And how do we test? By doing this experiment, by comparing the magnetic moment of the electron as we measure it to what it is by the calculation. But in order to do the calculation, you had to know the fine structure constant. And then, at that time, in order to know the fine structure constant, you had to know the gyromagnetic ratio of the proton. But you also needed to know the thing that I measured as a graduate student. So NIST hired me based on the fact that I had provided this this precision measurement, that I had proved myself as someone who can do precision measurements.
Right.
Not to remeasure that again, because that was done, but just, I had proved I had the right stuff to measure things that were at the limit of what was possible to measure. Because that's what we often are doing at NIST, is making the very best measurements of whatever it is that needs to be measured, because we're the ultimate.
You're the, what would you call it?
Well, some people have said we're the high priests of measurement.
Yeah, you could use that expression. Yeah, sure. Yeah, so
that's why I came to NIST.
Okay.
So the story, the sort of funny part of the story was that when I got my degree, the tradition was that the thesis student, me in this case, gave a party for everybody else in the research group to celebrate the fact that I'd successfully defended my thesis.
Yep.
And it was also traditional that at the party that the thesis advisor would say a few words. So he did. What I forgot to tell you was that was only part of my thesis.
Okay.
I did another whole experiment. Why? Because at that time, which was mid-1970s, we first started to have commercially available tunable lasers where we could change the color, change the frequency of the laser to be whatever we wanted it to be. And this revolutionized atomic physics because now we could excite atoms at will and do all kinds of stuff with them. And other people in the lab were starting to use these things, and I thought, that's the way of the future. What I've just done is the past.
Yeah.
So I went to Dan and I said, I'd like to do an experiment using lasers. I don't care what it is. I want to learn about this new stuff. And he said, sure. So we came up with another experiment, and I did that. So I had two different theses. The one was the best measurement of this one thing that had ever been made. It's still the best measurement.
Wow.
Nobody has repeated it since.
Wow. Wow.
And that was 50 years ago.
Yeah. Amazing.
And then this other thing, which was sort of today, nobody cares at all that this measurement was made, but it was my beginning, my introduction to lasers.
Sure.
So at this thesis party, he said, well, it's a really good thing that you did that second part of the thesis, because if you hadn't, if you'd only done the first place, you'd probably end up at a place like the National Bureau of Standards. And of course, that's exactly where I ended up a couple of years later.
Yeah. Wow.
And being here, again, has made all the difference in the world. Because based on the fact that I had done this precision measurement, I was doing things that led to the redefinition of the kilogram, like 30 years later. Yeah. But still, more than 30 years later, almost 40 years later.
Wow. Yeah.
But because I'd been doing these other things with lasers, they said, look, why don't you take a certain amount of your time and fool around with these laser things, see if you can come up with something that's good for measurement. And I thought, well, what would be good for measurement using lasers? And the answer was laser cooling. It was completely new at the time that I first came here. The same year that I came to NIST was the first experiments that demonstrated that you could cool something down with a laser, done by Dave, who was at that time in our NIST NBS laboratories out in Boulder, Colorado. And I thought, well, this works. I mean, there had been a proposal to do it a couple of years earlier, but I'd never seen it.
Right.
And now there was this paper saying we did it.
Okay.
And I thought, okay, great. They did it with charged atoms. That is, atoms that have lost one electron.
Right.
And the reason is it's really easy to manipulate ions, charged atoms, because they've got an electric charge and you can exert large forces on them.
Yep.
So I thought, I want to do this with neutral atoms.
Okay.
Because neutral atoms are what we have used and still use to define what we mean by 1 second of time. The definition of 1 second is a certain number of periods of oscillation of the radiation that corresponds to the energy difference between two spin states in a cesium atom.
9 billion something?
Yeah, 9.18, and I forget what the numbers are after that, but I've got it in my wallet because I always carry the wallet card of the fundamental constants of nature.
Yeah.
It's one of the things that NIST does, and I will give you one.
Oh, nice.
And it's the first thing on the list.
Thank you very much.
Is
wow. Okay.
The frequency of cesium.
Oh, there we go. So it is 9,192,631,770
hertz.
Hertz.
Right. And so we have defined that transition in cesium to be that, and that is equivalent to defining what we mean by a second.
Right.
And So I thought, well, neutral cesium atoms are what we use to define the second, and the limitation in how well we can do that has to do with their motion.
Okay.
So let's slow them down, and that means cooling them.
Right.
And so I started on laser cooling,
Okay.
and that's what,
Yeah.
the rest of my career has been
And
about.
at what point did you kind of discover that this was a thing? You said it was David Wineland who had written a research paper, was
And
it?
he was doing it for the same reason. He
Okay.
wanted to make better clocks.
Right. And was this when you started with NIST, or had you heard about laser cooling when you were in MIT?
Yeah, so I'd heard about laser cooling when I was at MIT.
Okay.
I'd seen this paper by Dave Wineland.
Yeah.
I'd also seen a paper by a guy at Bell Labs named Art Ashkin,
Oh, yes. Yeah, I read about him. Yeah.
and he proposed an idea for how you would slow down an atomic beam of neutral atoms and then trap them. And I had all the apparatus
Yeah.
necessary to do what Ashkin was proposing right there at MIT.
Wow.
So I went into the lab and set up what Ashkin was proposing to do.
Okay.
And I immediately recognized this is a lot more complicated than what Ashkin was imagining.
Right.
So his idea was so easy to say. I would say I eventually did everything that he had proposed in that paper with the help of students and postdocs. 10 years it took me
Wow.
to do the things that Ashkin had proposed.
From when you read about...
From when I first read about it
Okay.
and had all the equipment that Ashkin thought you would need.
Wow. So he just theorized in a paper. He never...
He never did that.
Yeah.
I mean, he did do experiments, and eventually he got a Nobel Prize for mainly the biological applications of what we call optical tweezers.
Mm-hmm.
So optical tweezers is basically it's a focused laser beam.
Yeah.
Focused laser beam can trap things like living cells, which is, I think, the main reason why he got the Nobel Prize, but it can also trap atoms.
Yep.
And it's being used today to trap atoms to do quantum computation, quantum computers.
Yeah.
And we use it routinely just to study cold atoms. Once we've got the atoms cold, but you had to get the atoms cold before you could trap them. But Ashkin came up with the idea of optical tweezers in that same paper.
Okay. And what did you, when you read it, it probably sounded counterintuitive initially, because when people think of lasers, they think of, James Bond, where he's lying on the, and there's a heated laser coming. At the time, what was your thought process? Were you like, this sounds mad, or I want to try and prove
Well,
this?
mainly I wanted to try because I knew how it worked. That is, they explained how it worked. So it wasn't, once you've heard it explained, you can see what the idea is. Basically the idea is if you've got a gas with the atoms going every which way, if you shine light in such a way that it opposes the motion of the atom, then the atom will slow down because the light exerts a force on the atoms. Now the problem is, the problem that laser cooling solves is that some of the atoms are going one way and some of the atoms are going the other way. They're actually going in all different directions. So that if you shine a laser in, some of them will be slowed down, but others of them will be heated up by the laser. And on average, the thing will heat up just as you might intuit. But the brilliant idea, and Wineland was part of that brilliant idea when he was a postdoc at the University of Washington before he came to the National Bureau of Standards. The brilliant idea is that you tune the laser so that it is not quite on the right frequency for the atoms to absorb.
Right.
So then you make it so that it's lower than the frequency that the atoms want to absorb, but only by a little bit. Okay. Now, if the atom is moving toward the laser, there's a Doppler shift. Because if you move toward a source of frequency, it looks as if the frequency is higher.
It's higher.
Which means to the atom, it looks as if the frequency is the right frequency to be absorbed.
Okay.
Because you've made it a little bit lower. So that atom will absorb from this laser beam and slow down. If the atom's going in the other direction, then the Doppler shift is in the other direction, further down, so it's less likely to absorb the light. So now if you bring in lasers from both sides, the atoms that are going this way will absorb from this laser, and the atoms are going this way, will absorb from this laser, and they all slow down.
So you're kind of trapping them. You're with the tweezer. So that's
Well, that has nothing to do with the tweezers.
Okay.
That just has to getting them cold,
Right.
which you have to do before you could do the tweezers.
Tweezers. Okay.
Because the tweezers don't hold them very strongly.
Mm-hmm.
Basically, if the temperature was even 1 Kelvin, which is pretty cold,
Yeah.
that would be too hot.
Yeah.
So anyway, we started working on cooling neutral atoms that way, and probably the thing that really made the reputation of this group was that we accidentally saw that the atoms were getting colder than what the theory said was possible.
Okay.
So you can easily work out the theory for the thing that I've just described, and it tells you how cold you could get the atoms.
Okay.
What the lowest, there's a lower limit. And the reason that there's a lower limit is because this process of cooling is balanced by another process of heating.
Okay.
And the heating comes from the fact that when the atoms absorb light, that they then have to re-emit the light.
Yep.
And that re-emission is in a random direction. And that randomness heats the atoms.
Okay.
Okay, it's a little more complicated than that.
Sure.
But by and large, it's because the randomness of what we call spontaneous emission, the emission of light from an excited atom, that's a random process.
Yeah.
And that randomness leads to heating, and the balance of the two things tells you what the temperature will be.
Right.
And for sodium atoms, which is the first atom that we laser cooled, that temperature is calculated to be 240 microkelvin.
Microkelvin.
So that's really, really cold.
Wow.
I mean, that's colder than anything had ever been made at the time.
Wow. So what would that be in terms of like Celsius, just to kind of give people
Okay, right.
perspective?
So well, it's almost impossible to give you a perspective based on Celsius.
Okay.
It's I mean, I could give you a number. It's minus 273.15 plus 240 millionths.
Of okay.
Yeah, okay. So, but that doesn't make any sense. The way I would like to describe it is this. Let's say that you wanted to explain to somebody how tall an ant was. You would look at the ant and see how high the ant is above the surface the ant is on.
Okay.
You would not ask how far below the top of the Empire State Building the ant is.
Okay.
And that would be what measuring it in Celsius would be like.
Right.
Because the 0 Celsius is like the top of the Empire State Building.
Yeah.
Okay? And the ant is where we are at
In terms of cooling.
in terms of cooling.
And then the pavement is absolute
the pavement
zero.
is absolute zero. So it only makes sense to talk about it up from absolute zero.
Okay.
Down from Kelvin, it's the same as zero.
Yeah. It's just not intuitive to try to do it from the other end. An absolute zero, from what I've read, is something that can't be achieved.
Yeah, so that's an interesting concept.
Right.
So most people will say that that you can't achieve absolute zero, and in a certain sense, it's true.
Okay.
So, but what does it mean? What it means is that if you're talking about a real temperature, now what do I mean, and why have I said a real temperature?
Yeah.
Temperature is really only defined in what we call the thermodynamic limit, a system that is big enough that the fluctuations that you might have by virtue of the fact that it's made up of a bunch of atoms, that those have been averaged out so much that you don't need to think about them anymore.
Okay.
Okay? If we have only 1 or 2 atoms, then you're definitely not in the thermodynamic limit, and it might not make sense to talk about temperature.
Okay.
Okay? So, let's say you're Dave Wineland, and he can cool a single ion down to the lowest possible energy level that it can be. In other words, what we call the ground state. So quantum mechanically, when we hold something in a trap, there's a lowest possible energy, and it's not zero.
Okay.
Because of Heisenberg's uncertainty principle and what we call zero-point motion, quantum mechanics guarantees that nothing ever is going to be static.
Okay.
that there's always going to be some quantum fluctuations, okay?
Okay.
But if you were actually in that lowest energy state, then that would be temperature zero, because temperature is only about the extra energy.
Okay.
Temperature is not about that quantum 0 point energy. It's about the extra energy.
Right.
Now, Wineland can do an experiment where if he tries to cool down an ion and then look to see what energy level it's in, 99 times out of 100, and I'm making these numbers up, but it's something of that order, 99 times out of 100, it's going to be in the ground state.
Okay.
Now, if you made a sample of atoms and they were all in the ground state, you'd say that was T equals 0.
Yeah.
Absolute 0. So if you make one and it's in the ground state and you've verified it because you've measured it, sounds like it's absolute 0, but it's not in the thermodynamic limit. It's only 1. In order to do the thermodynamic limit, you would have to imagine doing it again and again and again. But if you do it again and again and again, every once in a while, 1% of the time, you're going to find that that atom is in the first excited state, and that means the temperature isn't 0.
Okay.
In the sense of thinking about that absolute 0 is about things that are in the thermodynamic limit. But the fact is that we do so well that for many applications, it might as well be 0.
Okay. Okay. Interesting. Yeah, because they talk about, in quantum physics, things get, as Einstein said, things get spooky when you get down to that level, because things behave in a different way.
Things behave in a different way. But the thing that really freaked Einstein out was not so much that. I mean, he didn't much care for the Heisenberg uncertainty principle.
Okay.
But he was perfectly comfortable with ideas like, 0 point motion and that sort of thing. The thing that he sort of derided as being spooky was what we call entanglement.
Okay.
Now, entanglement, what is entanglement? And one of the reasons I'm going down here is because NIST, not me, but NIST has been a champion in the business of entanglement.
Yeah.
So,
nice.
Okay, so anyway, what is entanglement? So first, let's talk about superposition.
Yep.
So let's say we've got an electron, and it's in a magnetic field. And so it's got a spin. And the spin can point along the magnetic field or opposite the magnetic field. And one of the weird things is those are the only two possibilities. If you measure what is the direction relative to the magnetic field, there are only two possible answers. That's a result of quantum mechanics.
Yep.
And it itself is kind of weird already. Okay, but that wasn't what freaked Einstein out. What freaked Einstein out was, well, not even this. You can put the atom into a state where it is both up and down at the same time. We call that superposition. Now, first of all, just saying that sounds crazy.
Yeah.
I mean, because we always say you can't be in two places at the same time. That's not true quantum mechanically. Quantum mechanically, you can be in two places at the same time, or equivalently, you can be in two states at the same time. You can be up and down at the same time. Now, what does that even mean? Because that's so outside our ordinary way of thinking about things that it doesn't even seem to make sense. Okay, so what does it mean? It means, I would say, two things. It means that when I measure whether the thing is up or down, I will get either up or down, and I will not be able to tell you beforehand which of those things I get, no matter how much I know about it. In other words, I make this state, this superposition, by hand. I mean, I started with an electron that was spin up, and I did something to it to put it into this superposition of being both up and down at the same time. And I know exactly what it is. And in spite of the fact that I know exactly the state that it's in, I will not be able to predict whether I'm going to find it to be up or down.
Okay.
So that's part of it. The other part is, because I know exactly what state it's in, I can do something to it that'll put it so that when I do measure it, it'll always be up.
Okay.
Or always down. This is to get away from the possibility. I could say, look, maybe I just had a whole bucket of electrons, half of which were up and half of which were down, and I'm going to pull out of those one that I don't look at and give it to you, and you're going to, when you measure it, you'll get either up or down, but you won't know which. It's not like that.
Okay.
It's that this thing is in this very special state where I know exactly what to do to it so that when I do measure it, it'll always be up.
Okay.
But before I do that to it, no way I could tell whether it was up or down.
Right.
Okay, so I'm not sure if that makes more sense than before I said that. This freaked Einstein out.
Mm-hmm.
He said, no. There's got to be something
Mm-hmm.
that tells you, or that tells somebody, at least in principle, that God knows whether this thing is going to be up or down.
Okay.
In fact, he famously said that he didn't believe that God plays dice with the universe.
Right.
That that there must be something about this state that tells you whether it's going to be up or down.
Mm-hmm.
And this was one of the features about quantum mechanics that Einstein didn't like, and it leads to the uncertainty principle, which he didn't like either. Okay. And he constantly was coming up with ways of trying to see how you could beat it. And Bohr, a good friend of his, but also sort of his intellectual sparring partner, would come up with ways of showing, no, that doesn't work.
Okay.
That, because it's terrible. Sure. It's terrible that I can't remember such such a famous thing.
He'll come to you in a minute, I'm sure.
Podolsky.
Okay,
Einstein, Podolsky, and Rosen wrote this paper, and it often goes by the EPR for Einstein, Podolsky, and Rosen. Okay?
Right.
And now they've extended it to two particles.
Mm-hmm.
And they said, now they didn't say this, but this is the way we talk about it today.
Right.
Imagine these are two electrons, and one of them is up and one of them is down.
Sure. But
I'm going to make a superposition of having the first one up and the first one down, superposed having the first one down and the second one up. Okay, so it's a superposition, but it's a superposition of a two-particle state.
Right.
And Einstein showed that with such a state, if you then separated the two particles, so this one is particle 1, which could be either up or down, and this one's particle 2, and it could be either up or down. If you measure this one to be up, the other one's going to be down.
Okay.
And how can that be? How can it know to be down because it's so far away?
Yep.
Nothing can communicate between these two things. And it's a little bit more complicated than that. But basically, this is what he wrote.
Okay.
And said, this is just totally crazy.
Yeah.
Nothing could be this crazy. So quantum mechanics has got to be incomplete. There's got to be more to it because if all you've got is quantum mechanics, you end up with this totally crazy result.
Sure.
And nobody else had recognized this before. Well, Bohr wrote a response that everyone agrees was totally inadequate.
Okay.
So Bohr was not able to come up with an argument for why Einstein was wrong. And it just sat there. The vast majority of physicists thought this is a very technical thing that nobody really cares about. But in 1964, I think, a guy named John Bell, an Irishman.
Oh, yeah.
But working at CERN at that time, so in Geneva.
Oh, yes. Yeah.
Okay. Was doing particle physics, but he said, one of his famous quotes was, during the week, I'm a quantum engineer. I just do calculations that people need. But on the weekends, I have principles. And he started to work on this idea, trying to understand what it was that, on a more fundamental level, what it was that was freaking Einstein out, and why couldn't Bohr come up with an argument against it.
Okay.
And he came up with what we now call Bell's inequalities. Basically what it says is that if you've got this kind of system, and again, Bell didn't do it that way, but other people later on figured a simpler way of expressing what Bell did. If you had this thing with two particles, with the spins can be up or down, there's a correlation. If you measure this one, what's the chances that this was going to be up or down? And he could calculate, making a very simple assumption about the way the world works.
Right.
Basically taking Einstein's point of view, that there must be something that tells you that the thing's going to be up or down before you measure it.
Okay.
This is what's now known as the realism. In other words, that the property of something exists before you measure it.
Okay.
Sounds like a perfectly reasonable thing, right? Yeah. It's one of the first things we learn when we're children is when the ball rolls behind the chair, it didn't cease to exist, right? This is why peekaboo is such a great game for kids, because things disappear and they haven't gone away, right?
Yeah.
So the idea that something exists before you measurement sounds perfectly reasonable. The other thing is that something that happens here cannot affect what happens here if what's here is far enough away that a signal going at light speed won't get there in time to affect it. That's completely reasonable.
Yep.
Okay? So based on that, on those two completely reasonable things, which Einstein would have been in complete agreement with, and which Bohr would not have been in agreement with, because he would have said, no, there's no such thing as reality until you measure.
Okay.
He would have said the act of measurement creates the reality. And Einstein said, no, I can't buy that. That just can't be so.
Right.
So Bell said that if you believe with Einstein, then you'll get this inequality. But if you calculate what quantum mechanics tells you, it'll violate that inequality. And the difference is that now, instead of having this thing that Einstein said, this is just too weird, Bell has something you could do an experiment and measure the correlation between what you measure here and what you measure here. And if you get one number, Einstein is right. And if you get the other number, then Bohr is right.
Okay.
And nobody had understood this before. From 1935 to 1964, nobody understood this. And all of a sudden, there's actually an experiment you could do.
Okay.
So people started doing experiments. And the guys who did those experiments got the Nobel Prize a couple of years ago. Klauser and Aspe and Zeilinger. Okay? But there's always been a discomfort among people thinking about these things, that there are what we call loopholes. You see, the way they did the experiments is they had two photons, and they said one photon that way, one photon the other way, and they had photon detectors. Now, the trouble was those photon detectors were not perfect. A photon falls on it, you got a 20% chance that you get a click.
Okay.
And the rest of the time, you don't see anything. So you just throw those away. But when you get the click, then you say, when you're going to click on both of them, right, then you say, oh, great, okay, let's examine those. So with all those, it turns out it verifies the quantum mechanical prediction, not the Einstein prediction.
Okay.
But what if the ones you didn't detect behaved differently?
Yeah.
Or what if that's called the detection loophole?
Right.
Okay, that you have to assume fair sampling, but why should you assume fair sampling if you're going to assume that maybe quantum mechanics doesn't work? See, this is really fundamental. So you have to think about the most fundamental ideas.
Right.
Another idea was that what if when you make the measurements on these things, you have to, what you're measuring is the polarization of the photons, that is which direction the electric field is oscillating. And then you've got an analyzer that has a direction, and then you have to turn it in different directions. What if you turn it and somehow or other the one over here, the photodetector over here, has plenty of time to see, what direction that is, and what if somehow that affects it? Well, we don't know how that happens, but again, you got to think about the most fundamental things. So people worried about these loopholes.
Okay.
So come a hero, Sewu Nam, at NIST, and he develops these detectors that are essentially 100% efficient.
Okay.
So they're not like these lousy 20% efficient things that the first people did. These things are 100% efficient. I mean, maybe 99 point something.
Yep.
They're just amazing. The way they work is that a photon comes and hits a superconducting wire that is right on the edge of going normal.
Okay.
And the photon heats it up enough that you can tell, and I mean, it's even more wonderful than that. You can tell if it was one or two photons that hit it. You could tell if it was 19 or 20 photons that hit it. No other detector before was able to do that.
Wow.
These were amazing. And so they made an experiment in which they used these photon detectors plus ways of setting the polarizers so that you would set what direction they were in before after the photon had left the source, so it was only at the last minute that this thing would know what, but it didn't have time to know what it is, because you said at the last minute there wasn't enough time for a signal to get there. And other things like triggering that with a quantum random number generator, so you couldn't say, oh, you knew what it was gonna be. So all kinds of wonderful things, and did what's called a loophole-free experiment, and that was, well, I think it captured everybody's imagination, and that was a NIST thing. A couple of other places did it, but nobody as well as NIST.
Okay. And so what did that reveal then in terms
Well,
of
it revealed that finally you could put to rest that Einstein just had it wrong.
had it wrong about, because he said it can't be that crazy where as soon as something is measured, it reveals its spin.
It's reality,
It's reality.
whereas before it's measured, that reality doesn't exist.
Okay. And because some people think, because that is a famous, obviously, aspect of quantum physics, is that something can be two things at once, but then at the point of measurement that it stops that and it reveals itself.
Now, the two things at once, it's really just a way of saying it.
Yeah.
The only thing that really counts is what is the mathematical description of the thing. And the mathematical description is that it's not in one state or the other before you measure it. And after you measure it, it is.
Yeah.
And how did it get there? No one is capable of answering that question. How did it go from being both things to being one?
Yeah.
That's, I would say, still an open, but maybe a philosophical question.
Mm-hmm. Yeah.
We know how to do the calculation, and we know that the assumption that of both locality and reality is wrong. That is, Bell's calculations show that if you insist on local realism, that's wrong.
Okay.
That does not correspond to the way the universe works. Doesn't answer the question of how you go from one place to the other. It just says you cannot imagine that the reason you got that result was because that result existed before you measured it.
You can't be certain. Okay. And is that where the Heisenberg's uncertainty principle comes in?
I would say that the Heisenberg uncertainty principle is related to that.
Yeah.
But it's not exactly the same thing.
Right, because you can never, his thing is that you can never know the position and momentum of a particle?
Correct.
Okay.
Or any two what we call conjugate variables.
Right.
So they're like energy and time are similar conjugate variables, and you can't know both of them. And the degree to which you can't know them is Planck's constant.
Right. Okay. And in terms of like superposition, it's the act of measuring. Some people think that this is like a magical thing, but it's like photons of light. When you measure something, that obviously puts it causes it to collapse.
Yeah. So that's right. I hadn't used the word collapse, but that is one of the things that people often invoke here. So, for example, let's say you emitted a photon on Mars. And you manufactured the photon in a certain way so that it had a certain, let's not do it a photon. The reason I want to not do it with photons is photons all travel at the same velocity in vacuum, regardless of what their energy is. Let's say you do it instead with an atom. Okay, so let's say you're on Mars and you release a rubidium atom. I say rubidium because it's one of our favorite laser cooling atoms. Okay, we did sodium first, but rubidium works better.
Okay.
Okay, so you start with a rubidium atom and you arrange it so that this rubidium atom is in a wave packet that has a certain size when you're on Mars, and you shoot it toward the Earth. Let's say somehow or other, there's a scientist on Earth who's going to receive this this rubidium atom, but by the time it gets to Earth, the wave packet that was perhaps occupying a space that was on the order of micrometers on Mars, maybe, I don't know, I mean, I haven't put the numbers in, maybe it's the size of the Earth by the time it gets to Earth, or maybe it's the size of this room or whatever. But the person who's measuring it is going to measure its position to a micrometer.
Okay.
So how did you get from having a wave packet that extends over, say, the size of the Earth? What does that mean? It means that the atom is in a superposition of being everywhere, not just two places, but a gazillion different places all over the Earth, And then somebody measures it. And that measurement takes a microsecond. And there's no way that the collapse could have happened.
Okay.
So there couldn't be anything physical that corresponds to this wave packet. Just a mathematical description, because something physical couldn't collapse that fast.
Yeah.
So I don't like to even use the word collapse.
Yeah.
Just like to say that when you measure it, you get one of the results that are in the superposition.
Okay, one of the possible states.
Yeah. And before you measure it, you don't know where it is, and after you measure it, you do.
Okay.
And the property of being someplace was brought into being by the process of measurement.
Okay.
And that's a tough thing to accept.
Yeah.
Because it's not the way the world works
Yeah.
at the macroscopic level.
Yeah, but when you go to the quantum level, things are a lot different to up here at the macro level.
Exactly.
I guess. Yeah. To maybe circle back a little back to your initial experiments with trapping with lasers.
Yeah.
There was an interesting device that I believe that you built called the Zeeman slower,
Yeah.
and that was in the mid-80s.
Yeah.
Okay. Could you maybe expand a little on that?
Sure. So I often say the Zeeman slower was my one good idea. Everything else was luck. But the Zeeman slower was actually a good idea.
Yeah.
So here's the deal. What we want to do is take sodium atoms,
Yeah.
any atom, but we were doing this with sodium, and they have to be in gas form, because that, if they're metal, I mean, we're not going to be able to do anything with sodium metal. So they have to be in a gas form, and I have to heat sodium up a whole lot to get it to vaporize. So these sodium atoms are going to start off really hot. Okay? And that means they're going to have pretty high velocities. So in the experiments we did, the velocity in round numbers of these sodium atoms was about 1,000 meters per second.
Okay.
Now, if we're going to start to trap, we're going to have to get the velocity down to maybe 1 meter per second or less. Okay. I mean, in the end, we got a lot lower than that. So we got to slow these things down by a lot. And so the question is, how are we going to do it? Well, what Ashkin said was, well, you got the sodium atoms going like this in one direction, and you got the laser going with this, and all of the absorptions are in the good direction, so the beam is going to slow down. Sounded great, okay? But remember, I told you I went into the lab and I shined the laser into the sodium, and I thought, no, that's not so simple.
Yeah.
What I immediately realized was what was going on was this. The atoms that are going at the right velocity, so that their Doppler shift puts the frequency of the laser in resonance with the atoms. It's going to be some narrow range of velocities, a few meters per second range of velocities. Those atoms will absorb light and slow down, and then their Doppler shift will change and they will stop slowing down.
Okay.
Now, I said these atoms are going at 1,000 meters per second. What I didn't tell you was that it's actually a spread of velocities that are centered around 1,000 meters per second, but are about 1,000 meters per second wide. Okay? So that means that if I shine a laser beam in, there will be a tiny fraction of the atoms that are resonant with the laser, and they will change their velocity by a tiny fraction of their velocity.
Okay.
And that's not what we need. What we need is most of the atoms to change their velocity by almost their entire velocity.
Okay.
To bring it close to zero.
Right.
And that's not going to work the way Ashkin imagined it.
Okay.
The Zeeman slower is one solution to that. So now you put the atoms in a magnetic field. And you do that by winding a coil around the path of the atoms.
Right.
But you want this magnetic field to vary, the strength of the magnetic field to vary in space. So the way we did that was we had lots of turns here and only a few turns down here. So the magnetic field starts off really strong here, and as you go down the the magnet, it gets weaker.
Mm-hmm.
So what happens is the magnetic field shifts the resonant frequency of the atoms. So the distance between the ground state where the atoms start and the excited state where they go when they've absorbed a photon, that changes depending on where you are in the magnetic field, depending on how strong the magnetic field is. Okay, so let's say that you take the most probable velocity, which is on the order of 1,000 meters per second. And the atoms are in the place where the field is strongest.
Okay.
And then you tune the laser so that for that velocity and for that magnetic field, this laser is going to be absorbed.
Okay.
Okay. Now, so those atoms absorb the laser and they slow down, which means their Doppler shift is a little different. But they've moved. So their magnetic field is a little different.
Okay.
And you fix it so the two things cancel out. The amount by which the magnetic field shift, which we call a Zeeman shift, changes is the same as the amount by which the Doppler shift changes.
Okay.
So you compensate for the fact that you're changing the velocity of the atoms
Constantly. As it goes through the...
Plus, all the atoms that were at a lower velocity will come into resonance at a different place in the magnetic field. So you'll sweep all of the atoms from whatever velocity you start with. You'll take all the atoms that have a lower velocity and sweep them down to close to zero.
Okay.
Now, there's more to the Zeeman slower. With the magnetic field on, it makes it so that you are less likely to do something called optical pumping, which I haven't talked about yet. The sodium atom is not as simple as I've sort of imagined it to be. I was saying it had a ground state, had an excited state, and that magnetic field would change the difference between these two states.
Okay.
In fact, the ground state has two what we call hyperfine states that are different by a lot, by 1.77 gigahertz.
Sure.
And each of those states will be split up by a magnetic field, one into 3 different states and another into 5 different states. Okay. And the upper states are even worse. Multiple states separated by a whole bunch of different things and with even more magnetic sublevels. Okay?
Right.
So one of the bad things that can happen is you take a sodium atom in a ground state, and it might be in any number of different electronic ground states, but all these different 3 plus 5 levels. And they could be in all those levels, and typically they are in all those levels. And you excite one of those levels up to some state, and it'll come down to a different level.
Okay.
And the laser won't be able to re-excite it.
Right.
The Zeeman slower tends to fix all of that. The Zeeman slower tends to, when the atoms decay, tends to put the atoms into the highest energy level of all these 8 different energy levels. And then from there, it goes to the highest level in the upper state, just because of what we call the selection rules, the rules that tell what can an atom do when it absorbs light. And that simplifies the whole process and makes it possible to slow down most of the atoms. So the Zeeman slower does 2 sort of magical things. It gets rid of the optical pumping, and it allows you to fix the Doppler shift problem. Okay.
So it's constantly kind of adjusting for the change in the Doppler shift.
Yeah, automatically.
Automatically. Okay. So it's kind of like you're solving a problem that you're causing in the first place, as in, to put it kind of like you're putting them through this, it's like a tube, cylindrical tube, you're firing the atoms at the laser, and then the Doppler shift is constantly changing, so it's causing them to fall out of resonance.
Yeah.
And then you're constantly trying to update that so that keeps...
Exactly.
Yeah, I'm just trying to, for my own understanding.
There's another way of doing it, which we didn't invent, but we also put into practice, and that is change the frequency of the laser.
Right.
To compensate the change in the Doppler shift.
So fine tuning, is it?
Yeah, but you have to be changing the frequency on the fly.
Oh, so manually you have to be
it's too fast to do it manually. We have to do it electronically.
Right.
So we have to change the frequency by a lot in 1,000th of a second.
Wow.
But we learned how to do that.
Okay.
But the trouble with that is that it only works for 1,000th of a second, and then you have to start all over again. So it's not working continuously. The Zeeman slower works continuously.
Okay.
And that's one of its beauties, is that it just produces a whole lot of slow atoms
Right.
all the time.
Okay. And what, how did you, because it's a very kind of creative and pragmatic way to come up with a solution. How did you initially think of that?
I have no idea.
Yeah.
I was,
Did it come to
it's the way people come up with ideas
No,
for
it's-
anything. You sit down and say, okay, what can I do to fix this?
Yeah.
What can I do? And I already knew about this idea about changing the frequency of the laser, and I knew what its limitations were. And I said,
Yeah.
well, what else is there I can do? I could change the frequency of the atoms. How do I do that? With a magnetic field.
Yeah.
How do I do it? I just do a little bit of algebra and figure out what I have to do to make a magnet that does all that.
Wow.
And then we made that magnet, and then it burned out.
Okay.
And then we made another one, and it burned out. And then we made another one, and it burned out. That was the
Yeah.
hard part,
Wow.
was figuring out how to keep it from burning out.
Yeah. Wow. Okay. Because it's a very creative, practical solution. So as in that's another thing with scientists, is in there is a lot of creativity.
Yeah, but it wasn't nearly as creative as the idea for laser cooling itself. That was amazing.
Well, I mean, that's kind of, I guess it's sort of subjective. I mean, other people could look at the same one and say that's a very practical, creative thing. Maybe you're being a bit.
Well, okay, let me tell you.
Yeah.
This. So you may have heard of the Physics Olympiad. There's this international competition where different countries send teams of high school students to compete doing physics problems. Well, the United States physics team comes to College Park, which isn't very far from here. It's where the University of Maryland is. I'm often there at the University of Maryland. And so one year they asked me to come and give a talk to sort of just, pump them up, So, tell them about how laser cooling works and all that.
Yep.
And I find out that they were given the Zeeman slower as a homework problem.
Oh, wow.
So that tells you.
Yeah. Wow. So how was that presented to them? How was the problem?
I don't actually know. I didn't see how it was worked out, but basically what they had to do was figure out what the functional form of the magnetic field should be.
Okay.
In order to automatically compensate for the change in the Doppler shift.
Okay. So they say you have
It's
this
a simple algebra problem.
Really? Okay. Wow. And the process then, when you started making it, obviously you had to get your hands dirty and you had to go through a lot of trial and error.
That was the hard part, was making something that would survive. The problem was that we had to make a pretty big magnetic field, and that meant lots of current. And that meant the wires got hot, so we had to cool them. And the best thing to cool them with is water, but water conducts electricity. And insulated magnet wire isn't really insulated. One of the little things I learned, I thought, okay, they put varnish on these wires and it's insulated. No, there's a spec for how many holes it has in it. And normally that doesn't matter. Because if you wind something up, the chances that two holes are going to line up and short something out is practically zero. But when they're in water, then those holes are definitely going to talk to each other, and you'll have an electric current, and it corrodes your wires, and that's the end of your coil.
Okay. What was the timeline of from like inception of the idea of making that machine to finally having the final?
Yeah, well, that's a good question. I would say that a few years.
Okay.
Yeah.
Wow. Okay. And I guess he was a colleague, partner, Hal Metcalf?
Yeah.
So he was working alongside you for...
Right. So when I was at MIT as a postdoc, he was there as a visiting professor.
Okay.
And that's how we got to know each other.
Right.
I had met him at a conference many years before, but we didn't really know each other. But there, when we were together at MIT, we did some work together. In fact, we wrote a paper together that was, in my memory, distinguished because of the fact that we took all the data we needed for that paper in one day.
Well.
That almost never happens. He had this idea that if you we're exciting atoms from one particular level. You know, I told you about these 9 different levels,
Yeah.
or 8, or whatever. Yeah, 3 plus 5. Yeah, so 8 different levels. You pick one of them and do an excitation to one of the levels up in the electronically excited state. That as you change the magnetic field, the distance between those levels would change. So you could sort of follow it along. But at some point, he calculated that it would disappear. In other words, that you couldn't make the transition.
Okay.
Why? Just because of the way the quantum mechanics works out, that you think of the levels are actually superposition of 2 other levels. You see, the thing is that the levels have to do with the orientation of the electron and the orientation of the nucleus.
Okay.
And the nucleus has multiple different orientations, and so there's more states.
Right.
Okay? So, but as you change the magnetic field, the mixture of how much of, say, electron pointing this way and nucleus pointing this way compared to electron pointing that way and nucleus pointing that, that changes. And some of them will cancel each other out, and the transition will go away. Well, it was all straightforward. We had the apparatus, we did it, we published it, and we sent the paper in. Just one, it took us longer to write it than it did to take the data.
Yeah.
And today this phenomenon is well known, but this was very new at the time.
Yeah.
So people liked the paper, they published it. And this was the amazing thing. So this was in probably 1977 or so, 77 or 78, okay? After the paper came out, a few weeks, maybe a few months later, each of us got a letter from a German physicist named Hanley. Really a famous guy, very famous guy. Everybody knew what the Hanley effect was. Something that he had done when he was very young in the 1920s.
Wow.
That's the thing that made him famous.
Yeah.
Okay? And now it's the mid-1970s, and he's written us a letter saying, what a lovely paper. It's so nice to see that there are still new things to do with sodium in a magnetic field, because his work had been with sodium in a magnetic field. And we got this letter from this incredibly famous guy saying that we'd done something nice. I was surprised he was still alive. His work was in the 20s.
Wow. Yeah, that's crazy. I bet it was lovely to get that
It
letter.
was. It was an amazing thing to get that letter.
Yeah, because it kind of validates kind of what you're working on.
Yeah, yeah.
And did you say that paper you wrote before you started working on the Zeeman slower?
Yeah.
Okay. And
but you see, it had all the features.
All that, yeah. And so your ultimate goal with the Zeeman slower was you had the problem of the Doppler shift.
Right.
And this was ultimately what...
And the optical pumping.
Okay. And this is what would lead then to you ultimately being able to cool atoms and keep them at a certain...
Yeah, but if we hadn't had the Zeeman slower, we would have done it with the other kind.
Okay.
The thing we called a chirp cooler, because we did a lot of experiments with that. It's just that the Zeeman slower worked better.
Okay. Okay, so it was a more kind of practical solution to be able to...
And today, I would say the Zeeman slower is used in probably order at least half of the labs that do laser cooling.
Wow.
Use a Zeeman slower.
Okay.
So that's pretty cool.
Yeah, that is. Did you trademark it? Wow, that's And Hal, I had read Hal Metcalf, was he was saying that this might not work practically?
Well,
because the science.
No, I don't think that in fact, when we first started off, I had, I think, 4 different ideas for how to fix the Doppler shift problem.
Okay.
So one was the Zeeman slower, one was what we call the chirp cooling, where you change the frequency. The idea was out there. Nobody had actually done it yet,
right.
But the idea was there. And then there were 2 other ideas. One that said, let's bring the light in from all different directions. That way, the Doppler shift will be different depending on which direction the light's coming from, and everything will slow down. And the other was, let's put more frequencies on the laser. Let's take this single frequency of the laser and spread it out. So those are the 4 ideas. And so we're sitting around thinking, okay, what are we going to do first? And Hal said, let's do the Zeeman slower, because it sounds like it's more fun.
Okay.
So that's why we did it. And it was obviously the right choice. I mean, who knew when we first started what was going to be the right choice? That was by far the right choice. Other people did all those other things. We did the chirp cooling. Other people did the chirp cooling. It was popular for a while. Nobody does it today.
Okay.
Other people did what we call the white light cooling, where you make the thing broad. It's not really white. And the other one, I think we call it the white box cooling, because the way you get the light to come in from all directions is you build a white box around the atoms.
Okay.
And then you just shine the light in and it just goes everywhere. And people did that. And nobody ever used either of those techniques to do anything.
Okay.
They just showed it worked and went on because it wasn't very good.
Wow.
So, just because Hal said this is going to be fun, we chose the one that turned out to be the winner.
Okay. Brilliant. And then, so when you had that created, what did that then allow you? How did you then progress from there in terms of the laser cooling?
Yeah, so probably the next big thing that we did was magnetic trapping.
Okay.
So people had talked about trapping for a long time. The ion people were doing trapping every day. It was easy to trap ions, as I said. They could easily trap ions at room temperature or above. And we knew we were going to have to cool well below 1 Kelvin to do any kind of trapping at all. But trapping was certainly one of the things that we wanted to do because, well, it was going to be the lead in to who knows what else. But I'm not sure that we really understood that well what any of this was going to lead to, other than that we wanted to make better clocks.
Okay.
If we had very carefully understood and worked on what kind of a clock we were going to make, we probably would have given up at the beginning.
Okay.
Because from what we knew at the start, we couldn't have made a clock. But we didn't. We just said, hey, this looks like it's going to be a lot of fun. It's got to be good for something. Let's do it. And we made the best clocks in the world.
Wow.
Well, we didn't, but using our techniques, people made the best clocks.
It paved the way for people to be able to
and
do
today
that.
I would say all top-notch clocks use some of the techniques that we invented.
Wow. And you said that's a mad statement to be able to make, but it's pretty cool.
Yeah.
It's
well, one of the things I'm really proud of is you might know that time for in the United States is kept by 2 different agencies.
Right.
NIST,
Yep.
our people in Boulder keep time for the country. Civilian time. Military time is kept at the U.S. Naval Observatory, which is in Washington.
Okay.
And if you go there to their laboratories, they have laser-cooled clocks just like they have in Boulder.
Oh, wow.
All of the guys who run that clock laboratory at the U.S. Naval Observatory were postdocs with us before they went there.
Amazing.
So the whole clock thing for the Navy is created by postdocs from our group.
Wow. That's very cool.
Yeah. So I really think we did what we promised we would do.
Yeah.
And a lot more.
Yeah. So you said when you were setting out to experiment with laser cooling, you didn't want to limit yourself to saying we're going to make better clocks, because that probably limits your thinking and your creativity.
We probably weren't thinking that clearly. All
Okay.
I think we were thinking was, this would be really cool if we could do it.
Yeah.
And one of the things might be that we'll make better clocks, but it's really cool. And if you do something that's different and cool, you're probably going to learn something new.
Yeah.
In fact, there was one of the famous guys, I think it might have been Wolfgang Paul, not Pauli, who was even more famous, but Wolfgang Paul, who was one of the people who proposed that you could trap atoms magnetically, but didn't really succeed in doing it.
Okay.
He said something along the lines of, in order to learn something new, you have to do something new.
Right.
And what we realized we were doing something new, and so we felt confident we were going to learn something new, and we did. We just didn't know what it was until we got there.
Yeah. And the key is to kind of keep going, because some people, I guess, if they don't know what direction they're headed in, they can be like, am I wasting my time?
Yeah, that happens. But we had the rare good fortune, which seems to have continued, that things worked better than they were supposed to.
Okay. Because usually it's the other way around.
Exactly. So Murphy's Law tells you that it's always going to work worse.
Yeah, the opposite.
But for us, it worked better.
Okay.
And it happened again and again. And so I don't know, somehow or other we're charmed, or the field of laser cooling is charmed, that, I mean, the first thing was that the temperature was colder.
Yeah.
By a factor of 200. Cesium atoms were gotten 200 times colder than what the predicted cooling limit was.
Okay.
And those were the atoms we used for our clocks.
Right.
So it really was a big deal to get cesium atoms below 1 microkelvin.
Okay. Wow.
If we hadn't done that, we wouldn't have been able to make the kind of clocks that we did.
Yeah.
So, but then later, we stumbled upon what we call optical lattices, Bose-Einstein condensation. We came into that. I think we were the 9th group to get Bose-Einstein condensation, but that was a NIST thing.
Okay.
The first Bose-Einstein condensation was in the NIST laboratories in Boulder.
Wow.
And they used a lot of the techniques that we developed to do it. But so we were a little bit later. But again, the whole idea of Bose-Einstein condensation, it gives you a bunch of atoms almost at absolute zero, almost for free.
Okay.
So you cool it down enough, and boom, a large fraction of the atoms are effectively at absolute zero. What could be better than that?
Okay.
And it just seems like things like this keep happening, and we keep rolling along. So it's like, it's like a locomotive. We just keep rolling and doing incredible things.
Wow. And so the cesium atoms, so those were used previously before your work, is that correct, in atomic clocks?
Exactly.
Okay.
Since 1967,
Right.
the second has been defined to be what you see on your wallet card. The first cesium clocks were made in 1955 at the NPL in Teddington.
Okay.
The first atomic clock, on the other hand, was made at NBS, then in Washington, D.C., in 1949. That was the first atomic clock.
Wow.
And it wasn't until 1967 that they finally changed the definition. But the first atomic clock was actually a molecular clock. It used ammonia.
Right.
But anyway, so why cesium? People often say, why cesium? Remember, when they made the first cesium clock, there were no lasers.
Yeah.
Okay, so why cesium? It's the heaviest alkali. Okay, it's not radioactive, or at least not very radioactive. Francium is more radioactive, but cesium is not radioactive at all. And so, being the heaviest, it means it has the biggest hyperfine frequency. That frequency of 9 gigahertz, that's the highest of all the alkalis.
Right.
Like hydrogen, I think, is 1.4. Sodium is 1.7 gigahertz. Lithium, I think, is less. Anyway, and why is that important? Because the higher the frequency, the smaller fractional shift you're going to have
in seconds
when something bad happens.
Right.
Like if there's a little bit of magnetic field, it'll shift the atoms by approximately the same amount, no matter which atom it is. So if you have a bigger frequency, that's better. And there's a number of effects like that are going to be better.
Okay.
Being the heaviest atom, it means for the same temperature, it's going slower. Because temperature is kinetic energy. Kinetic energy is mv, 1/2 mv squared. So higher mass, lower velocity to be at the same temperature.
Sure.
The vapor pressure of cesium, that is how much cesium, in a sense, boils off when you heat up the metal, is the highest of all the alkalis. We'll have to heat up sodium a whole lot, a little bit more than room temperature, and I got a lot of cesium atoms. So that means they're not going to be going so fast because the temperature isn't very high.
Okay.
Cesium atoms were easy to detect because it has the lowest ionization energy of any of the alkalis. So it doesn't take very much energy to kick off the valence electron that's doing all the work.
Yeah.
So it turns out that if a cesium atom hits a metal that has a work function. Now, what is the work function? It's the amount of energy it takes to liberate an electron from the surface. So what'll happen is the electron would rather be inside the metal than on the cesium atom. So the metal sucks the electron off the cesium atom, leaving a charged ion, and that ion is easy to detect.
Okay.
And you have to detect these atoms somehow.
Yeah.
So all of those things were in favor of cesium. And then when we started to do laser cooling, it turns out that cesium is one of the best atoms to laser cool.
To cool. Okay.
Yeah. So that's like a gift from God.
Wow. Yeah. So it was already being used. And to kind of maybe break it down into simple layman's for people about atomic clocks. Why do we use atomic clocks? What is an atomic clock? Could you maybe just give a quick sort of, because some people might be, they hear the expression or they hear the term atomic clock, but they're like, that sounds kind of like some sci-fi sort of thing. What would be your kind of quick sort of definition as to why it's important and what it is?
Before we defined what a second was by the atomic clock, the definition of a second is what you probably would have thought the definition of a second ought to be.
Yeah.
It's a fraction of a day, where there's 24 hours in a day and 60 minutes in an hour and 60 seconds in a minute. So that's a certain fraction of a day. Well, it's not that easy. It turns out that what a day is not that straightforward. The solar day, that is the time between two places where the sun is highest in the sky, that's the length of a solar day. That changes by 15 minutes during the year because of the tilt of the Earth and the ellipticity of the Earth's orbit. Now, the astronomers had that all figured out long ago. So there's a thing called a mean solar day, and there is a mean solar position. In other words, there's a place where the sun is in the sky on average. And the astronomers had figured all that out. What they hadn't counted on was that the day changes for other reasons. The tides slow down the Earth because they're like a friction force, okay? The ocean currents affect the angular momentum of the Earth. And because of conservation of angular momentum, if you don't have a friction force, which you do, that means that if you increase the angular momentum due to the ocean currents, then you're going to have to decrease the spin. And so ocean currents are changing earthquakes, redistribute the mass, and that changes what's called the moment of inertia. How far away from the center various masses are, because earthquakes change where stuff is in the Earth. And all of these things change. The Earth has got a liquid core. It's rotating. When that changes the rotation of the Earth. So the Earth is not a very good clock.
Okay.
And by 1900, there were better clocks than the Earth. And that what that meant was you had ways of measuring things, mechanical clocks, which eventually became like quartz clocks. I mean, probably your watch has a quartz crystal in it. And that's a very good clock, better than the Earth. And those quartz clocks became de facto time standards because the Earth wasn't good enough. So when you got atoms, now the trouble with the quartz clock is every quartz crystal is different.
Okay.
So, and what do you calibrate it against? The Earth isn't good enough. So you needed something else. If you were going to make precision measurements of time or frequency, you needed something other than the Earth. And that was atoms, because atoms, as far as we know, never change.
Okay.
But of course, I say atoms never change, but how do you know?
Yeah.
And the answer is we have people at NIST in Boulder who are checking this out.
Wow.
So people like Jun Yi and Anna Maria Ray, collaborating with Mariana Safronova, who's at the University of Delaware, these people have figured out, what if the fine structure constant isn't constant? What will it do to our atoms?
Okay.
And then they measure different atoms against each other and see if they're... This is amazing.
Yeah. Wow. Wow. So the and then obviously when they settled on cesium, because it's a reliable...
Yeah, for all those reasons that I gave you.
Yeah, it's a reliable...
cesium,
And it's the oscillations that get counted.
Yeah, it's the oscillations of the microwaves that induce a transition. So a simple way of thinking how atomic clock works is this. Imagine you start with a cesium atom, and just imagine the cesium atom is simpler than what it really is, that it's got a nucleus and it's got an electron.
Right.
And what we're going to do is, when the microwaves have the right frequency, we're going to flip the electron.
Yeah.
And how can I tell that the electron got flipped? Because the cesium atoms will go in a different place
Okay.
in a magnetic field because the magnetic moment of the electron will be opposite if it flips, and I can tell that by the force that the magnetic field exerts on the that'll change sign.
Right.
Okay, so I can tell when it flips. So now I start with, say, the cesium atoms like this. I shine in some microwaves. I keep turning the frequency of the microwaves until, boom, that happens. When that happens, I know that frequency is the one that the cesium atoms want to absorb.
Okay.
It's more complicated than that in reality.
Okay.
But
And once you have it in that state, then that's when you use that as the base unit of the second.
the base unit is that frequency that made it change.
Okay.
That's the thing that's the essentially that's the ticking clock, is that microwave oscillator that made it change. When you got it adjusted so it makes the atom change, then you know that the microwaves are ticking at the frequency that's on that card.
Okay. Gotcha. And
So
then
it's not what the atoms are doing, you see. It's
that change.
it's that
transition.
it's that frequency. Now it turns out that the trick we use to make things work better is we put the atoms in a superposition of the two states.
Okay.
And when they're in that superposition, then the atoms do tick
Right.
at that frequency.
So they
but
just
it's the superposition that ticks,
Okay.
not the atom in one state or the other. It's when it's in the superposition that the atom, in a sense, ticks at that frequency difference between the
Okay.
two states.
And it's very reliable when it's at that state and temperature, and nothing else will really influence that.
Well, except for all the things that do.
Yeah.
And that's what the people who make those clocks,
Yeah.
how they earn their living is by measuring and controlling all of those things. So a little bit of magnetic field will change it.
Okay.
The temperature of the room will change it because the temperature of the room is radiating infrared radiation, and that changes.
Right.
If the atoms collide with each other, that shifts the frequency. There's a whole litany of effects, and the people who make the clocks have to chase them all down.
Okay. Gotcha. And then, so when you got the atoms to that level of temperature, just slightly above, a smidgen above near zero, that means like they're reliable in terms of they're as still as they can be.
Yeah, and it improved the performance of the clocks by
Okay.
approximately a factor of 1,000.
Wow. So that, and then to kind of move that into kind of modern day applications, what would be the most important application these days? Is it like GPS?
Well,
That's
probably GPS is the most important application that everyone is sort of familiar with.
Yeah.
And were it not for atomic clocks, we would never have had GPS. So when the first people in 1949 made the first atomic clocks, I'm sure nobody was thinking of GPS.
Yeah. That was
But the existence of those clocks, what they were thinking was, we need to make measurements of things, and we don't have a solid standard. That standard is moving around, and that's not tolerable. We got to fix that. But once you had clocks like this, then people could think, hey.
okay. Now what can we
Now
do?
remember, this is now years before the first satellite went up.
Yeah.
Because, GPS relies on the fact those atomic clocks are in satellites.
Yeah. Wow. And so the because GPS initially was made by the military, I believe, the US military, and
Well, I think it still is.
yeah,
I think it's maintained by the military.
maintained by the military. Okay. And so they did have atomic clocks at the time, but
Yeah.
now I guess the current atomic clocks that have been enabled by your work and research, I guess allows for a much smaller margin of error.
Yeah, so this is rather subtle.
Yeah.
There are no laser-cooled clocks in orbit.
Mm-hmm.
Actually, that's not true. In the International Space Station, there are laser-cooled clocks, but only for research purposes, not to run the GPS.
Okay.
So the clocks that are in GPS are sort of ordinary clocks.
Right.
But on the ground, you've got clocks that are controlled by the the laser-cooled clocks
Okay.
that are then controlling the satellite clocks. So the satellite clocks have to be updated all the time.
Okay, so they're synchronizing with the...
Yeah, and so they're synchronizing with clocks on the ground, which are connected to the laser-cooled clocks. Plus, you also have to know what the orbits of the satellites are. And having good clocks on the ground helps you to do that better. But you see, it's sort of a second-order thing. It's not like it's just we had better clocks and we put them in GPS. Now, there will probably come a day when those kind of clocks are in GPS. But there's so many things that GPS has to worry about. When you propagate through the ionosphere, the fact that the ionosphere is moving shifts the frequency and the phase of the... So you have to send signals at several different colors of, or it's, several different frequencies, I should say, to cancel out the effects of what the ionosphere is doing.
Okay.
So there's all these different things that all have to be done in order to make it work better when you have better clocks. But if you didn't have better clocks, you wouldn't be able to do these things better.
Yeah, because nowadays, obviously, its GPS is accurate to within a meter, feet, or even less.
If you're willing to wait long enough, you can see continental drift
Okay.
at like a centimeter per year.
Wow.
So, but you have to wait for a long time to get rid of lots of, basically averaging out the kind of noise that you would have under ordinary circumstances.
Sure.
But sort of quickly, it's good to, I don't know, I don't really know, but, probably meters or tens of meters.
Yeah.
But one of the things that NIST is working on is portable atomic clocks. I mean, things that are chip size, not just things that you would put in a suitcase, but things that you could put into a phone.
Wow.
And so they developed, again, out in Boulder, these guys are making chip scale clocks.
And is that something, do you think, that will be in the next few years?
It's already happening. There's already companies that are making chip scale clocks.
Wow.
And selling them.
Okay.
But they're not at the level of the best clocks, but this is coming.
Wow.
I don't even know. You may know more about what John Kitching is doing in the latest.
I usually cover EO.
But so those miniature, those are using laser cool?
No.
Cool? No, they're not.
Not yet.
Okay.
But probably the next generation will.
Wow. Okay. And so the laser cooling, how much has that advanced in terms of other scientists have probably picked up on your methods?
Yeah. So I would say that today, the field of what we call AMO physics, atomic, molecular, and optical physics, is dominated by laser cooling.
Okay.
But most of those people probably don't think of themselves as doing laser cooling. They just think of laser cooling the same way they think of a screwdriver.
Right.
It's one of the tools that you've got handy
just
that you
take it for
use
granted.
in order to make the next step in your experiment. But I would say that probably the majority of papers that are being published in this area, somewhere along the line, they used cold atoms.
Okay. And just back to a bit of GPS, like the discoveries in laser cooling to get it much more accurate for GPS and other things. Does that relate to like Einstein's relativity in terms of?
Yes. So first of all, I would say that nobody other than scientific users are using clocks at their very best.
Okay.
But what we have found historically is that when you make a better clock, it doesn't take too long historically before somebody says, yeah, I'm going to use that. So, for example, one of the things that's not so obvious to a consumer is these clocks are used to synchronize communication. So if you want really fast communication, one of the ways of doing it is that you have synchronized clocks on both ends of your communication, and you distribute the bits of information according to when they arrive. And the only way you can do that with the necessary accuracy is to have the very best atomic clocks. So that's a commercial application that isn't so obvious compared to, say, GPS.
Yeah. Because when you need, I guess, sub-millisecond communication.
It's like nanoseconds.
Nanosecond. Yeah, it's crazy when you dig down into it. And because a lot of people, this is kind of just caveating into Einstein's theory of space-time.
Yeah,
as
that
well.
comes in
Yeah,
big time. So here's another story that I like to tell.
sure.
When I came to NIST in 1978,
Mm-hmm.
the best clocks in the world were, not surprisingly, NBS clocks, okay, in Boulder. And their accuracy, that is, they believed that they were getting the right cesium frequency to a part in 10 to the 13.
Okay.
Now, nobody else in the world was that good. So there wasn't another clock that was that good.
Mm-hmm.
But if you had had a clock that was that good here in Washington, then you would have been just barely able to detect or not detect. It would be just at the limit of being able to detect Einstein's prediction for how clocks change their frequency in a gravitational field.
Okay.
So Einstein predicted that the lower you are in the gravitational field, in other words, closer to sea level,
Yep.
you'd be lower in the gravitational field than you are in Boulder.
Mm-hmm.
The lower you are, the slower the clock runs. It's sometimes called the gravitational redshift.
Yep.
Okay?
Okay.
And the effect at, near the surface of the Earth is a part in 10 to the 16 per meter.
Okay.
Now, the clocks were only good to a part in 10 to the 13. And Boulder is 1.5 kilometers higher than Washington. And when you combine two things together at a part in 10 to the 13, then the relative uncertainty is going to be 1.4 times 10 to the minus 13, and the expected effect is 1.5 times 10 to the minus 13. So you can see you're not going to see it.
Mm-hmm. Yeah, it's minuscule.
Today, the clocks can resolve that much difference in height
Okay.
due to Einstein's theory of general relativity.
Right.
So we can now use clocks to do geodesy, to map out the gravitational potential of the Earth and see maybe a deposit of something valuable, like some, I don't know what they look for. Oil, gold, diamonds, rare earths,
Yeah, yeah.
So yeah. And today the best clocks have a reported accuracy, which it's a little bit funny, on the order of a part in 10 to the 18, a little bit better than a part in 10 to the 18. Now that's not real accuracy because they're not cesium. Cesium is only good to a few in 10 to the 16. So that when I said 3 orders of magnitude, going from part in 10 to the 13 to part in 10 to the 16 is that 3 orders of magnitude. But there's another 2 orders of magnitude by using different atoms.
Okay.
And the international community is in discussions. What is that next one going to be?
Okay.
And I'm betting on NIST.
Wow.
I'm betting on Genie.
Yeah. So what atoms do they have atoms now that are proving to be more accurate?
Yep.
And those are which ones are?
Strontium is one of my favorites.
Okay.
Ytterbium, but also some ions. Dave Wineland, I think, has the best. Well, I don't know. They're almost the same. Aluminum ions at below a part in 10 to the 18. But which one is going to be the one we're going to choose? Well, one possibility is we won't choose.
Okay.
That will make sort of a conglomeration of a number of different atoms. I'm not in favor of that myself, but that might happen.
Yeah.
Which of the others to choose? Well, you might say the one that people have gotten the best results on. Well, but not necessarily, because some of them are easier to work with than others. The lasers that you need may be cheaper or at least easier to use. So there's a lot of things that are going to go into the decision about what atom to use. So we're having international discussions right now about that.
Debate on that, and that could then in the future be used to be the base unit.
So we might find that first line on that table will disappear, and a new one will be for a different transition.
And it would be
with more digits,
higher frequency. It could be.
It'll be a higher frequency,
millions of times.
It'll be several times 10 to the 14 or low 10 to the 15 hertz.
Okay, trillions of
Something,
trillions.
which is, I don't even know
Yeah.
what those numbers are
Yeah.
called, but it'll be optical frequencies,
Yeah.
like visible or near ultraviolet.
Wow. And just for people kind of to explain that kind of, a big number is needed because that means you can break down a second into an even smaller.
Well, I would say the real reason is that all the little effects that have about the same size and frequency will now be a smaller fraction
Yeah.
of the
Yeah, so that corrects errors, or that's much more. Okay.
Yeah, it'll be a smaller fractional error. Yeah.
It would be remiss of me to not go into quantum computing.
Yeah.
Are you going to that? You guys have been having a great conversation.
Oh, yeah.
You've been at it for like 3 hours.
Oh,
And
is
I
it
do
that?
have to
It is
pick
5
up my
o'clock.
kids from daycare.
Oh, really? Okay.
So,
Wow.
would you mind wrapping up?
Oh,
I just
yeah,
don't
sure.
want to be late to pick up my
Yeah,
Yes,
sure.
no, that's very important.
Sure, yeah.
Okay, so let me just say in 1 minute, laser cooling, we had no imagination that one of the applications down the road would be quantum computing. But in order to trap an atom in a laser, in a laser tweezer, in order to have an ion in its ground state and to have its motion so small that it doesn't mess up the frequency of the operation of a qubit, these things have to be cold.
Okay.
And so laser cooling is essential for the atomic ways of doing quantum information. The superconductors, that's a different story. That's not laser cooling. It's a different kind of cooling.
Yeah.
Dilution refrigerators. But everybody who's doing ions or neutral atoms, they rely on laser cooling.
Okay.
And we never imagined that.
Okay.
I think we better quit.
So that's the next application of it with quantum
Well, it's
computers.
one of the many applications.
Yeah. Wow. Amazing. Yeah. I mean, like we could talk all day, but yeah, no, time flies when you're in flow. But no, this has been a great chat, Dr. Phillips. I really appreciate it.
But if you have to go, I can probably escort him out. Actually, there's probably not. I can escort him out. I'm trained.
Is that okay?
There's like the foreign escort training.
Yeah.
For
Would that be all right?
Yeah.
The time was.
Yeah, it's.
But it's funny because we're talking about time. But yeah, sorry, I was saying it would just be obviously the application of cooling atoms and applying it to quantum computers these days. There's multiple different types of quantum computers that they're trying to develop at the moment.
Yeah,
one of them
and
is.
I would say the three big platforms, as I see them today, are the superconductors. So this is where you make some kind of a SQUID device.
Sure.
That stands for superconducting quantum interference device, which involves a Josephson junction, which is a quantum device. But the thing that's quantum is the superconducting state of these electron pairs in certain kinds of metals.
Okay.
Or certain kinds of things become superconducting. So that has nothing to do with what I do. But it still needs to be cold because you only go superconducting when it's really cold, and you need to get rid of all of the thermal excitations, or as much of the thermal excitations as you can. And so they try to get as cold as they can.
Right.
So it's really important to be cold. But for ions and atoms, that is charged atoms and neutral atoms, which are two of the other important platforms, just in order to make them behave, to have their properties be well understood and be stable, they need to be cold. They need to be in the ground state of their trap, because otherwise, when you do an operation, it's going to not be predictable what the result of the operation is. But if it's in the ground state, then it's a predictable thing that you can do. And that's the kind of thing that why you need for ions and atoms to be really cold. But then there are other aspects of what we call quantum information science. It's not just quantum computing.
Okay.
We do a quantum simulation. So we have a physical system, and we want to understand the nature of this physical system, but we don't want it to be perturbed by thermal problems. That is, that's going to be an additional complication that'll make it harder to understand the physical system. So
Sure.
we make a physical system that's made with laser-cooled atoms. So it's almost like having something at absolute zero.
Right. Okay. And you're saying there's in the quantum computing aspect, there's the trapped ions quantum computer. There is, I guess there's one that probably leans a bit more towards your research as well. Neutral.
Yeah, the
atom
neutral atoms, that's essentially using the kinds of things that our group and other groups, I mean, we're not the only group that was in on the ground floor of laser cooling. Steve Chu's group at first at Bell Labs and then at Stanford, and now he's at Berkeley, I think, or maybe back at Stanford, because he went to Berkeley to become head of the Lawrence Berkeley Laboratory, but I think he's at Stanford now.
Wow. Okay. And just with quantum computing, it's the very early stages of it.
I would say so.
Yeah.
I would say that it is still at the early stages, but within the time from when it started, I think of the starting point for quantum computing as an experimental science being 1995.
Right.
So that's 30 years, right?
Yeah.
So it's advanced tremendously in the last 30 years, but I think we're still in the early stages of what you would like a quantum computer to be.
The practical applications of it.
Yeah. Now, some practical applications, like solving physics problems, which I see as being a practical application,
Yeah.
we're practically there. But factoring numbers, I mean, that's sort of a spy thing, because factoring numbers is related to public key encryption. And to do that is going to require a lot more development of quantum computers.
Yeah, because people also say that about quantum encryption, that they're scared that people are now gathering data from classical computers.
Yeah.
In the future, then they're saying we might come up with a quantum encryption that can decrypt that.
Well, right. There's a quantum processor
Yeah.
that can decrypt it. So people are now using what's known as quantum proof, or, quantum, in other words, encryption methods that cannot be broken by quantum computers.
Right.
And NIST has been a leader in that.
Okay. And is that something, it's like to do with the no...
Post-quantum, that's it. Post-quantum encryption.
Okay. Because is there like a no replication rule or something in physics?
That's for quantum key distribution or quantum communication.
Right.
So that's a different story, but it is a way of beating quantum decryption.
Okay.
So let's say that you were sending something through public key encryption, then if somebody has a quantum computer, they can break that code.
Okay.
Let's say instead you were communicating using what's called a one-time pad. In other words, you come up with a bunch of random numbers and you deliver that set of random numbers to somebody else that you're then later going to communicate with. That's not breakable.
Okay.
As long as you only use the pad once.
Right.
Okay? Because basically there's no way anybody can figure out how to decrypt that.
Yeah.
Because it keeps changing. It's not like it's a cipher where you can always, that 1 is always equal to A. That it's not that.
In binary, it's you're trying to mess with these atoms that are in a superposition, and then whatever it reveals.
So what we do is, for quantum communication, is you send probably a photon that is in an entangled state where Alice, the sender of the information, sends one pair of an entangled pair to Bob, the receiver, and keeps one. And then before either one of them measure it, it doesn't exist, remember?
Yeah.
Okay? So if there is an eavesdropper, known as Eve, who captures the photon that Alice is trying to send to Bob, Eve cannot reproduce a photon and send it to Bob at the same time that Eve measures it. Because of this quantum no cloning theorem, it's not possible to make a copy of an unknown quantum state. And this is an unknown quantum state because until the measurement's made, you don't know what it's going to be. So Eve can't capture that thing, measure it, and then send on to Bob something that would be the equivalent of the entangled state that he should have gotten, because that's just not possible by the laws of physics. So you could create a one-time pad by this kind of quantum communication.
Okay.
And then that would be unbreakable.
Right. Okay. Yeah, I think there's a long way to go in quantum computing. People are like, what would be when do you think it'll get to a point where it can?
Well, I have a colleague who used to be my boss here, but he's now a quantum consultant in the private sector. But we have a bet, and the bet is about when we will have a quantum computer that can factor numbers that people care about. And by that we mean a number that cannot be factored by a classical computer given a year of operating time. So imagine there's some future time where there's some future classical computer, and think of the number, the product of two big prime numbers, that number cannot be factored by the computer of that era, of that future era, but can be factored by a quantum computer. And the question is, when will that be? Okay, so what we've decided is on the year 2045. And the bet is, will we have a computer then or not? And we've taken opposite sides of that bet. I'm betting we won't, and he's betting that we will. And when I talk to people who are in the business, I usually find, and ask them, which side of the bet do you want to be on? I usually find that it's about even. So I think it's not a bad prediction that we've got about a 50% chance of having that kind of a quantum computer by 2045. Now, you've got plenty of people who will say, oh, we're going to have that in less than 10 years. I don't believe that, but we'll see. Now, 2045, I'll be dead. But if it's 2035, I might still be alive.
You never know. Science.
I'd be pretty old.
It's an interesting thought experiment, because there's obviously the race in quantum computing now with China and US and all these tech companies and trying to gain quantum supremacy, like the Sycamore chip with Google. But I mean, that whatever calculation that beat was
exactly.
Yeah.
Those calculations are not calculations that are particularly desired.
Yeah.
From a commercial point of view. Now, I'm not saying that they're not interesting, but to do something. So a lot of people will say that right now you don't have a quantum computer that does anything interesting that couldn't be done by a classical computer, and that's either correct or almost correct. But I think we're very close to having interesting problems that can be done by quantum computers. Certainly, we're very close to doing interesting many-body physics problems.
Okay.
Things that because you see, the trouble with many-body physics is that, well, depending upon the problem, let's take a very simple problem, what we call a spin chain.
Yeah.
So we've got a one-dimensional array of say spins. They could be atoms, whatever. And we want to understand how this thing works. And the things we have to add in are things like, well, how does one spin go from one site to another? And what kind of interactions are there between the spins? So for a sufficiently complex version of this, the problem gets twice as hard when you add one more spin.
Okay.
Because what you're doing is you're adding a place where the spin could be either up or down, and that doubles the number of possible states. And so you've made the problem twice as hard by adding just one spin.
Okay.
And that's why many-body physics is really hard, because the difficulty of doing it grows exponentially. And when I say exponential, I mean an exponential function, not just something. A lot of people use the word exponential when they mean big. I mean it's an exponential function. It's, 2 to the n is the number of different states if I got n spins.
Right.
Okay. So it's an exponential size. And a quantum computer can handle that, but a classical computer can't. So doing many-body physics is certainly one of the things that I think is on the near horizon for quantum computers or...
Right. Okay. And so it's kind of, there's a lot of hype as well that's happening, but that's just to try and get people into the kind of zone of thinking about. But
well, what is the reason for hype? You got all these quantum computing companies that are worth billions of dollars that don't have a product that is actually going to make money for the person who buys it.
Yeah, true. It's kind of at that hype, very early hype phase. I just, sorry, I know that you've got to go soon, but maybe what we can do is just some closing remarks. Like you've always been a curious mind, and you don't get into experimentation for not necessarily one specific end goal. It's kind of to see where it'll lead. Is that? I would say that not only do I get it just, for the curiosity, but because I know from the historical development of science that doing things that advance your understanding of science without knowing what the application will be are the things that make progress. Okay.
I often say quantum mechanics was developed 100 years ago.
Yeah.
Schrödinger and Heisenberg wrote their papers essentially 100 years ago.
Yep.
What has been the most important fruit of quantum mechanics for people's daily lives? And I would say it's the transistor. Semiconductor electronics have changed the lives of almost everyone on Earth. And there's no way that Heisenberg or Schrödinger or Bohr or Born or Jordan would have been able to predict the transistor based on what was known in 1926. Just so far beyond. But, it was 1947 when, so only 20 years after that, you had the transistor. Now, even when you had the transistor, you probably couldn't predict the integrated circuit that would have a trillion transistors on it.
Yeah. Well, yeah. So it's you go into it with not knowing what you might create down the line.
Exactly. But if you don't do it, you're never going to get there.
Yeah.
So if we want to continue to have new things that change our lives in the way that quantum mechanics has done it, then we're going to have to work on things that are just blue sky research. If we don't do that, we'll never get the good stuff.
Yeah. Things that you're unsure of, but you enjoy, and you just keep pushing at that. And then, so what would you kind of leave as a closing remark with any kind of young scientist these days, any budding scientist, because you've achieved a lot of great things, and Nobel Prize, and everything else. What keeps driving your curiosity beyond that?
Yeah.
And what would you kind of give?
Well, the advice I usually give is just what you said. Stay curious.
Yeah.
That's and do what you love.
Yeah.
Now, these are so trite. Everybody says this.
Yeah.
But it's true. It's trite because it's true.
Yeah. Yeah, sure. So you just keep pushing at what you enjoy and don't think about the accolades. Because if you do something for the accolades...
Oh, yeah. People sometimes ask, what do you have to do to get a Nobel Prize? And my answer to that is wrong question.
Yeah.
The right question is, what do you have to do to learn something new?
Yeah.
What do you have to do to have fun doing it? That's what you should do.
Okay. Because it'll shine through if you're doing something for the money, or if you're doing something for the accolade. People will see, people are clever, people will see that. But as you said, if you keep pushing for the curiosity and just for a pure passion, that's how you'll get somewhere. I guess, am I getting that right?
Well, yeah, I would say that if you want to have a satisfying career,
Mm-hmm.
then the thing you should be thinking about is not the accolades, because
Yeah.
sometimes that will come and sometimes it won't.
Mm-hmm.
Think about what will teach you something new, what will allow you to have fun while you're doing it.
Mm-hmm.
My motto is that a good day is a day when I learn something new,
Mm-hmm.
not a day when, you get a prize.
Yeah.
The good day is the day when you learn something new.
It's the journey. It's people think, oh, if I got this sort of accolade, I'd be really happy. But I think it's, again, trite, but it's the journey, the discovery of it.
Well, it's the discovery. It's the fact that you learned something new.
Mm-hmm.
I mean, the satisfaction of seeing for the first time something that no one else has ever seen.
On Earth, yeah.
I mean, the first time that we trapped atoms,
Mm-hmm.
that was amazing.
Yeah.
Here, there it is on the chart recorder.
Mm-hmm.
We've trapped atoms for the first time ever.
And then we've broken physics and gone against the textbooks to freeze it to way below what
And the
theory
fact
said.
of the matter is, if you're a research scientist, you have days like that all the time.
Yeah. Wow. That's amazing. That's really good advice. It's simple, but it's something that people sometimes find hard to follow. But no, this has been a really great chat.
And
Phillips,
if
appreciate
you're
it.
a person who funds research,
Mm-hmm.
then you want to make sure that that kind of thing happens in the laboratories that you're responsible for, that you are nurturing.
Mm-hmm.
Amazing laboratory director that I had,
Mm-hmm.
Catherine Gebbe.
Yep.
4 of her people got Nobel Prizes here at NIST.
Wow.
Yeah, under her watch.
Okay.
And people would ask her, as you could well imagine, what is your secret?
Yeah.
And what she said was something that other people would say, but that she actually did.
Mm-hmm.
And that was hire the best people. Give them the resources they need.
Mm-hmm.
Get out of their way.
So just give him that, let him do it, and don't micromanage, don't get in it. Okay. That's good advice. That's
And
good
look
advice.
what happened.
Brilliant.
4 Nobel Prizes. But
Mm.
other things like all of the top clocks in the world using the things developed
For sure.
under her watch.
Yeah. Wow. Yeah. I don't think you can get more satisfaction than that. To know the people that you've fostered.
Yeah.
Brilliant. Brilliant. I'm very enlightened and inspired. This has been a great chat, and I'd love to come back again someday.